All right. So, yeah, so it's my great pleasure to have all of you on board. Um, so, um, my name is Debarati Chatterjee. I am professor at the Inter-University Center for Astronomy and Astrophysics, which is located in Pune, in India. I'm one of the organizers of this meeting. The other co-organizer is Professor Anuradha Gupta. She might be here already, or otherwise, it is a bit of an unearthly hour because she's at the University of Mississippi. So I hope she will be able to join us later. Um, all right, so talking about the motivation behind organizing this meeting. So during the pandemic, when I started working as a chair of education and public outreach for the LIGO-India project, I came across a lot of young early career researchers in gravitational wave astronomy in particular, who are contributing to the field, but many of us didn't know about them. So we introduced this a section of the LIGO India blog, Gravity Matters, which is called Glorious Women. So maybe I can show you glimpse of this blog if you can see my screen. So we highlighted many of the contributions from such women researchers at different stages of gravitational wave astronomy, different stages of their career. And in particular, later in 2024, when I attended the first LIGO Virgo Kagra collaboration meeting, this is the first time I saw many women across the collaboration, across many countries, who were in many leadership roles. And this is when we were motivated to organize this particular event, where we can highlight contributions at various career stages from women in this multidisciplinary field. So I look forward to these 2 exciting days when we'll have a lot of brainstorming and discussion over this topic. Um, so in today's program, so I will just run by quickly by the program today. So we have first plenary session, which which spotlights eminent speakers across the different collaborations. This will be followed by a panel discussion, which is on particularly focused on women representation in gravitational wave science. So stick with us. Tomorrow, we will also have a focus session, which highlights multidisciplinary aspects of gravitational wave astronomy, and followed by an interaction session where young students will be able to discuss and ask about career advice, about many tips and tricks from early career researchers who are contributing to this field. So without much ado, let's get started with the first session. So let me hand over to our first speaker, who is Professor Archana Pai. Archana, could you unmute yourself and put, can you
Hello.
yes, yes, we can see
Yes.
you. So I
Right.
will stop screen share so that you can share the screen. So Professor Archana Pai is, she's professor at IIT Bombay in India, and she's also the current PI of the LIGO India scientific collaboration. So she has been one of the leading figures in gravitational wave astronomy in India, and we are looking forward to hearing from her about her journey and also about her research field. So over to you, Archana.
Thanks a lot, Debrati. I hope I'm audible.
Yes, but right now we see a blank screen.
Oh, you cannot see my screen? Okay, just a moment. Let me.
I think when you went full screen that it went blank.
Okay, okay, wait. Just let me just check. Let me just. Yeah, let me share it again.
Sure.
Let me know. Is it
We can see
visible?
this second slide now.
Yeah, okay.
It disappeared again. I think if you go to full screen, maybe can you just not put full screen? Just I think it
Okay,
just
okay.
was.
Let me just do the following. Okay, let's
Yeah,
see.
now we can see it.
All right. Um, you want me to present like this? Wait just a moment. I think it's not allowing me to. Are you okay with this? But this will be.
This is fine because if you put play, I think it goes blank.
This should be okay. Yeah.
This
We can
okay?
move. Yeah.
Okay,
This
all
is
Yeah.
right.
Yeah.
fine. Yeah.
All right. Okay, fine. Good evening, good morning, everyone. I know that people are from different time zones here. Myself is Archana Pai, and I am a professor at IIT Bombay. And I'm currently the PI of LIGO-India Scientific Collaboration. This is one of the group of LIGO Scientific Collaboration. In fact, through that, all the people who work in India for LIGO Science, we work under this umbrella. So I'll just give you a little bit history about how the gravitational wave research sort of began and evolved in India. So in 90s, essentially, there were two leading groups, uh, largely, one was in Ayuka, which was under Professor Sanjeev Dhurandhar, largely focused on match filter searches, and they did work on diverse areas where even I got my training. Um, uh, uh, right from match filter searches to stochastic gravitational background searches, hierarchical searches, LISA, time delay interferometry. So there is large spectrum of topics the group sort of evolved. And then there was another work group which was in Raman Research Institute, developed on, largely on waveform development, and later on evolved into doing some testing GR. Yeah, with the in gravitational wave astronomy. Now, eventually, in 2008 to 2012, the whole thing sort of evolved into a consortium, because that time there were only two isolated groups, and several people like me who had got training during our PhD or postdoc phase, and then went to various groups abroad. Sort of we all returned, and we were sort of we took up the faculty positions in different institutes, and we thought that we'll form a consortium. The whole idea of the consortium was to have some vibrant gravitational wave community in India, and also growing community with the vision, or with the hope of bringing eventually a detector in India. So this Indigo consortium, in 2011, submitted the proposal for LIGO India, and subsequently joined the LIGO scientific collaboration in 2012. So during the discovery, the consortium actually evolved into with 9 research institutes, and there were 37 authors on the discovery paper. You can see the group of people who were working under Indigo Consortium. And I think there are some organizers. I can see Anuradha here. I think she was a PhD student, and I think later on moved as a postdoc in Ayuka during that time. So that was the group in 2016. Of course, all of us know that the spectacular discovery of gravitational waves from binary merger event, namely 1509-14, essentially started the field. And some of us contributed, namely to testing GR, endeavor with this event, and that sort of boomed, and that gave sort of lot of excitement in India. So much so far that, I mean, you can see here, I mean, this was the clippings of various newspapers which covered extensively the discovery. In fact, this is one of the rare things happened in India, where the scientific discovery got sort of cover page, in a newspaper, and in different languages. You can see that. And subsequently, the Prime Minister announced in principle approval of the LIGO India project. There was also greeting came from him after the discovery, which you can see here. So it was all exciting. And as a result of that, I mean, in order for the community, to grow, that was the goal. The Indigo Consortium eventually transitioned into LIGO India Scientific Collaboration. So this is the current, representation of the LISC. Here you can see that. So there are total 17 institutes all over India. With total number of members are 114, and then the authors on the LIGO Virgo collaboration papers are 79. And different institutes actually work on different aspects. So the core LIGO India institutes are IUCA, there is IPR, Institute of Plasma Research, RRCAT, which you can see in Indore here, which is located here. IUCA is in Maharashtra, you can see here, in this part. Right, and then there are several other institutes. So in Mumbai, we have two institutes. One is TIFR and IIT Bombay. So we do transient research. In TIFR, there are waveform developments. There is work on cosmology, lensing. Also in Pune, people work on extreme matter, like for example, like Debarati. Also, there is a lot of research on developing algorithms, lensing, again, testing GR, cosmology, stochastic gravitation waves. In ICTS, TIFR, people develop, there is work on developing numerical relativity waveforms. Also, there is a lensing work and testing GR. There are new groups which are formed. So the one in Calicut, which is NIT Calicut. So these are even the younger faculties we have, and we are sort of expanding to include more and more smaller colleges and new institutes. So NIT Calicut is one of that, and there is another college which is this Government Victoria College in Palakkad, where we have a LISC group now. Uh, there are also groups in Chennai, Chennai Mathematical Institute, as well as IIT Chennai, where there is also some experimental work goes on. And then, of course, there are institutes in Calcutta. Okay, so you can see that the whole LIGO India scientific collaboration is actually spread, and and in order to grow, I think there is various activity happens, like conducting workshops in different parts. Closely, I think people from the core LIGO India institutes are also now having some hands-on workshop in different colleges, and eventually we expect that some of them will actually join and contribute to the LIGO science. So this is a little bit about the LISC. So what I plan to sort of do for maybe next 5 to 7 minutes is, since our group was involved in the gravitational wave research for a long time now, and as you all know that with more detectors now, we have detected many more transient signals, right? So, for example, there are 4 observation runs I have completed, and in total we have seen close to now 400 compact binary mergers. With every observation run, the sensitivity of the detectors have improved, and that is what has culminated into the a large number of transient sources. So in our group we do a lot of work on developing transient algorithms. So for example, this is the famous picture of masses in stellar graveyard, where you can see each stick essentially corresponds to a compact binary merger event, where you have two component masses sort of merging into a final remnant. And this is sort of a summary of all these objects which we have seen so far. Now, the ones which you see on the top, which are basically the objects which are more and more massive. So as the detectors improve in the low frequency band, we are seeing more and more massive compact binaries. So we, in our group, we actually, work on trying to sort of develop specialized algorithms for these kinds of systems. So I'll just spend maybe 5 minutes just telling you what kind of things which we do. So just to give the background, so when we talk about compact binary, coalescing compact binaries, these are essentially two compact objects, largely neutron stars or black holes, right? So they are in the binary orbit, and as they evolve, they emit gravitational waves, and then they come close to each other, eventually merging, and then final remnant is sort of ringing. So that's what we call it as this in spiral merger and ring down phase, which is finally stitched together, and we try to look for signatures of that kind of signature in the data, right? Now, this is a typical waveform which you see. So this is a in spiral merger and ring down. I've shown you different representation of binary signal. So if you have, let's say, a spin is not aligned with the orbital angular momentum, then there is a spin orbit modulation or the precession, which you can see in terms of these modulations and so on and so forth. So in general, the morphology of the signal, when it goes to, let's say, higher and higher masses, it can be quite complex because it has more complex physics, which gets sort of into the signal. Now, there are two types of, searches, or, two types of looking for this transient, this thing. So, for example, I think if I can play a little video, so you can see that there is a tiny signal in this blue noise. And if you have some template, or if you have some knowledge of what kind of signal you're looking for, okay, then one can run a cross correlation between the two, and if this information or this template matches well with the signal, then you can see the signal sort of adds coherently, and you can see a peak, and the noise will add incoherently, and then it sort of the signal stands out. So this is what a standard, it's what we call it as a match filtering. Now, this is provided you have knowledge of the template. So if you have, let's say, your template is characterized by many multi-dimensional parameter space, namely spins, masses, the source location, the orbit orientation, and so on and so forth, then one can run this through a stack of templates and try to find the signal. It's almost like trying to find a needle in the haystack. Now, there are other approaches, so which we call it as a model agnostic approach, where where you're looking for basically excess in the time frequency representation. So if you have a signal, what you do is you try to get a time frequency representation of the signal, and if you and essentially if the signal can be represented as some excess energy, excess power in this time frequency representation, and one can combine this information in a more phase coherent way and try to develop clustering schemes to identify the event. Okay, so we have been working on this, both the approaches, for a while now. So Gayatri was a PhD student with me. So she was working on this approach. In fact, she improved. So for example, if you go for more massive compact binary mergers, then it looks almost like a blob because you do not see much of a in-spiral phase information, and as a result this blob can you know you can it can get confused with the noisy transient. So she developed some specialized veto techniques, which we used in this coherent wave burst, wavelet based model agnostic search, which was very useful because subsequently, when the first intermediate mass binary merger event was detected, I think with those improved techniques, the significance of this event was really good. Okay, currently, so I'm quite happy to showcase her work, because especially we are meeting together to celebrate the work from the women, young members. So she completed the PhD in our group, and then subsequently now she's a postdoc. She did one postdoc in Florida, and now she's a postdoc in Milwaukee. And she's doing quite well in the burst group in the LIGO scientific collaboration. So there is another kind of work which we do now, is again sort of uh, expanding on this signal noise discrimination sort of techniques. So here you can see, for example, if you have an intermediate mass binary signal, then it looks like a blob, and this is a noisy transient. So we developed this sort of a post-processing sort of step on this coherent wave burst, which is called as a Gaussian mixture modeling. So what you can do is this coherent wave burst, which is a model agnostic search, it has its own attributes, which sort of captures some time frequency morphology of various signal, transients, noise transients. And what we can do is we can develop this multi-dimensional, Gaussian mixture models. It sort of identifies this Gaussian. It sort of fits the multi-dimensional Gaussian sort of distributions. And using that, one can sort of try to improve on the existing model agnostic searches. So that's what we have been now doing it. We have applied this now especially on this all sky short duration transient signals. So which are sort of including, I mean, can be a sort of supernova event or transients and things like that. So we have done it on this simulated data, and currently this has been applied on this on the offline searches. So these are my two current PhD students. So there's Shayantan Ghosh, who has been working closely on this, and now there is another student who has joined this effort, and we hope to sort of improve these searches further. There is another work which we do again along the same lines, where we try to classify this using machine learning based approaches, where we use this convolutional neural network with transfer learning to try to distinguish between different kinds of glitches with respect to the intermediate mass black hole binary transient. So Kriti was a BTech student. She was an undergrad student. She developed this, this sort of model where we tried to separate the IMBH more of a edge-on kind of systems because that has information of higher modes and this approach seemed to be sort of doing well where we constructed some some new some veto kind of statistic, okay, which when we apply on the match filter based approach, we seem to be getting a very good improvement in the existing match filter based searches. So this work is, yeah, it's already published. I mean, we have not implemented it in the current searches, but this approach looks promising. And the last piece which I'm going to talk about is the work by one of by my postdoc. So Shubhagata Bhaumik, she has recently joined our group. She did her PhD in University of Florida, and her PhD work was actually focused on searching eccentric binaries, black hole binary signatures in the LIGO data. In fact, she was one of the lead person who ran the search for the eccentric black hole coalescence in the third observation run. And this she did it during her PhD, so it was quite remarkable. And she developed a very specialized sort of veto using some injections and in the time frequency representation where she could distinguish or she could separate the noisy transients or as opposed to the actual eccentric injections. And using that, I mean, this search was carried out. I mean, unfortunately, we have not detected anything, but she has developed a lot of expertise in this regard. All right, so I think that sort of summarizes the transient search. I think since I'm sort of representing the LIGO India scientific collaboration, I would like to speak a little bit about LIGO India itself. So the LIGO India is going to be the third LIGO, which is getting constructed in Maharashtra, in the central Maharashtra. So this is not very far from Pune and not very far from Mumbai either. And we are all very happy about it that the third LIGO uh, will be here. And some of us actually worked on the science case for LIGO India. So as you may know, so if you have, let's say, if you take the detector network, so for example, you have two LIGO detectors. There is an Indian detector, the LIGO India, what we call. There is a Virgo detector, Kagra detector. And if you just, these are basically the light travel time between the two sites, okay, measured in milliseconds. So you can see that the LIGO India forms, the Indian detector forms a very long baseline pairs, right? And that gives a good ability to localize the source. So that's the main the main takeaway of bringing the Indian detector. So for example, if you have two LIGO detectors in US, then and if you observe the source, then you can see these purple bananas. But if you include the LIGO India in a network, then you will be able to localize the source very well. So that's the key science goal. The detection rates also you'll improve because you have an additional detector in the network. Currently, the LIGO India construction is we are expecting to start very soon. Just few days ago, the tender was sort of given to the construction company, and we hope that everything should sort of take off very soon. So I think with that, I will just flash our group who is part of this LIGO India scientific collaboration and LIGO scientific collaboration. And thanks for listening. Thank you very much.
Thank you, Archana, for this wonderful talk. We will have some time for a couple of questions which are on the chat. So I'll read that to you, Archana, and you may answer them. So this one is from Divijyoti, which says, with the full approval to LIGO-India project, is there an effort to expand to more institute across India?
Yes, yes. So that is a plan. So we are sort of trying to, we are trying to, we are advertising to other institutes, whether there is any interest. I think we also try to sort of, in various scientific conferences, meetings, we do showcase LISC and the work, and we do encourage people to sort of, join. So there is an effort, which is ongoing effort, yes.
Yeah, thank you. And the second question is from Shafaq Ilahi. They say, what are some of the biggest contributors to sensitivity improvement from O1 to O4?
Okay, so I think I may not be the right person to talk about that, but I think if I know that there was a laser power was improved. Also, I think the suspension was improved. So these two, I think I'm sure I know about it. And of course, yeah. So the key contribution was, so there was squeezing was included in O4. So because of which the O4 sensitivity, the floor was sort of at the low frequency went down. So that was a key improvement in O4.
Yeah, thank you so much, Archana, for your presentation and being part of this
Yeah, thanks a
symposium.
lot. And I should congratulate to all of you who have organized this. I think it's a great effort. Okay, I'll try to, unfortunately, I have to leave because I have a class now, but I'll try to join tomorrow, maybe in the evening, some discussion session. And I wish you all a great event. And once again, congrats for having such event. I think it means a lot to many people. I'm sure I think they're going to get advantage of this. Thanks a lot. Yeah.
Thank you very much for taking time out. So I think with this nice introduction and talk about LIGO-India scientific collaboration and also highlighting women in the gravitational wave group of Professor Pai, next we can move on to our following speaker. So Professor Lee from University of Western Australia. Could you share screen and also maybe unmute yourself?
Yeah, can you hear me?
Yes, yes.
Share screen. Not quite sure which one to share. Hopefully you see what is. Yep.
Yes, we can see it now.
It's funny, it's not from very beginning. Anyway, yeah. So thanks for inviting me. I'm just going to for this talk, I'd like to talk about the Australians' contribution to gravitational wave. I'm from University of Western Australia. Did the screen also have my? Is that better?
Yeah, that's good. We can also see your cursor.
Yeah, good. So I'm from University of Western Australia, and I'm part of the AusGrav. That's our my title about AusGrav. I'm going to give an overview of the Australian gravitational research history briefly, and something about what AusGrav do, and then finally I'll give a little bit introduction of what our group doing. I'm an experimentalist, so I'm probably talking a little bit more from experimental point of view. I think I can't go to next slide somehow. Okay, good. So everybody know that the first detection in 2015, that is about generations of hard work. And that's a glory moment, but we have to remember there's so many people in front of us that did the hard work. I would like to, we know the Nobel Prize winners, and that they made a huge contribution. And there are also some very prominent pioneers like Rondriva and Brzezinski, who unfortunately passed away and couldn't be, in the Nobel Prize. And we also have Jim Huff in UK that made a great contribution, and he was later being knighted by UK, acknowledged. And in Australia, we also, the Australian government also recognized the contribution from the Australian consortium that they, in 2020, the Prime Minister's Prize for Science was awarded to the gravitational wave researchers. There are some 4 leading researchers. So you saw some graph. I presume you all knew what interferometric gravitational wave, how does it work? And there's this incredible technology and sensitivity, and they have very high vacuum and high precision optics, and incredible sort of control systems, very advanced. And also we have a very, from last talk, we have a advanced computing and data analysis science in the whole gravitational wave research community. For gravitational wave detectors, when I say incredible, and you can see that sensitivity change. This is probably the curve that sort of answer last question about this is from not 01, but it's from 03 to 04. And I pointed out is that with the squeezing that the sensitivity increased a lot. But then we have to understand that this is sort of a typical curve, and the low frequency basically is control and vibration oscillation, and the middle frequency is thermal noise. And then the high frequency is probably over there, it's a short noise. And the short noise is sort of related to the laser power and the laser. So if we increase laser power and you slowly sort of increase the sensitivity, and also if you apply the squeezing technology, then basically you can even dig in deeper, fully use the take advantage of the high power. And we all know that from then on, then this curve keeps going up. Then for our instrumentalist, we are trying to make this bucket, we call it a noise bucket, lower and lower, and then these more events will be showing, because there's probably lots of events buried in the noise. And for the data analysis people to dig it up. And for the current detectors, we all know there's in the world map, we have current LIGO, Virgo, and also we have LIGO-India coming up. But I have to bear in mind that we in Australia, we also have ambition if we want to have a Australian detector in the world map. I'll talk a little bit more. You see that the previous talk about the sensitivity, sky localization with LIGO-India will improve a lot. And if we add Australian detector, that will be, superb, from a line into a dot, so we can localize the event much better. So Australian gravity wave research is way back. is over many decades of research. We have contributed quite a lot before. From the very start of the LIGO, we started to participate with the LIGO collaboration. And in the first gravitation wave detection announcement, the Australian, you can see that the announcement said the discovery, which is published, they don't publish this in this paper, this was made by the LIGO scientific collaboration, which included a geo collaboration and Australia Consortium Interferometric Gravitational Astronomy. So Australian contribution is a big chunk for the first detection of the gravitational waves. And going back a little bit, that for the early, I don't know what you can see on the screen. Anyway, for the early gravitation research, it's in the 1990s to 2000 just about. And there was this bar detector. I'm not quite sure how many people knew about it. And the bar detector basically is like two mass connected. If you put it simply, it's connected with a spring. And then when gravitational wave pass, and this one will ring. Of course, it's a bar, and also the bar can deform and it will ring. So from the Weber bar to the world network of gravitational wave bar detectors, which including one in Australia, actually it's in University of Western Australia, that there's they did 20 years of research, and this have developed very precision measurement technology. It's a very beautiful engineered and transducer system, and but there is no detection. The sensitivity is not big enough. As I think it's about 10 to minus 19, and also it's narrow band. But from this research, they set an upper limit of, from that limit, we can't detect gravitational waves. And since then, if we move to the gravitational wave, interferometric gravitational wave, so the acknowledging in the first LIGO detection announcement we call ASIGA, and it was formed. Oh, I don't know what. It was formed in 1995, and when we started to do LIGO started to gravitation interferometers, and then in 1999, and we have actually established a LIGO, that's observatory. But of course, we haven't got an observatory, but that's our dream. And now we actually have a facility which is located at Jingjing, Western Australia. It's called High Optical Power Facility. I'll show you a bit later. And as I mentioned before, in this decades, ASIGA contributed to many development of advanced technology for LIGO, which some key contribution make the first detection, possible. So for when we first say this LIGO detector was we hoping that this little detector will expand it to a longer arm, and this is only 80 meters. It was located in a little bit north of Perth, where the university sits, in a bushland, in a nature reserve. We're still having it, it's still operating, and many technology was developed in it. And we are still testing some technologies. And then in 2016, just after the first gravitational wave detected, and the Australian Research Council, ARC, and founded a Center of Excellency for Gravitational Wave Discovery. and we call it OSGRAV. That's from 2016. And that by then it was about 4 universities, leading universities. And over the years, and there's more universities joining. And in 2023, there was the second OSGRAV funding was in place. And then now we have 7 universities and have you can see our goal is still for discovery, one detection, and then of course we need instrumentation. We have experimentalists doing optimization of the current detectors and also develop technologies for future detectors. And of course, and we still in the center, we have people doing gravitational wave astronomies and cosmologies and extreme matters. And I'm just, since we are celebrating women's contribution, and in OSGRAV, in first OSGRAV, it's about starting about 100 members, 1/5 are female. And now we have the second OSGRAV, now we have about 300 members, and 1/4 are female. The female number is indeed increasing because we have, although the proportion seems doesn't increase much, but then if you get the number right, and this is a great big chunk of the OSGRAV are females, and from senior leaderships to middle career and early career researchers, and lots of brilliant research, young researcher and postgraduate PhDs. And there's many, I can't possibly put all the photos in here. So just to feature a few in OSGRAV, you probably see that Vaishali was probably featured in LIGO-India, and she did a postdoc in ANU and made a great contribution with squeezing. And now she is working at the Royal Institute of Technology in Sweden. And also we have Chiara, who is, I think Chiara is probably in the audience now, and she did a PhD in Belgium, and she is now a research associate at the UAA, and she's a great experimentalist and a leading experiment at the Jingjing facility I will just mentioned. And then we also have Natsini, who is recently, probably not so recently, but still about a year, graduated from a PhD, graduated from Australian National University. And then now she spent extensive time at LIGO doing squeezing to help LIGO with the squeezing technology. And then now she's going to a defense industry. And also we have here with Tegan, who is only graduated, PhD graduated from Monash University a few months ago. And then now she moved to Princeton University and is still working on the black holes and neutron star binaries and the gravitational wave astronomy. Although here I want to emphasize with current LIGO and detectors, and because we have such a good sensitivity already, and there's a huge amount of data and astrophysics, gravitational waves, astronomy, then there's quite a lot of people working on that aspect, but we still have quite a lot of women experimentalists, which is probably traditionally is very not in a very popular area. We have brilliant female experimentalists. Now I'm just going to I flagged this out just because I want to talk about the experimentalists very care about all these curves. And people sometimes just say, okay, if you say this, if we want to increase the sensitivity at the high frequency, why don't you just, we have enough laser power. Why can't you just crank up the power? And then naively, you can say, okay, I'll just increase power, then sensitivity will get done. It's easy. But in fact, there's lots of other issues related to the power. Once you increase the power, all the other effects will kick in. And that's why one of the contributions the UWA research group actually did. I'll dig into a little bit of detail. So at UWA, we mainly do instrumentation, and we do, as I mentioned, we do this. We have this high optical power facility in the bush. It's about 90 kilometers from per city, and also we do quantum measurement and trying to reduce the quantum noise or beating the quantum noise in future detectors. And if you want to learn more, and here is our website. And in UWA, we also have a small team doing multi-messenger astronomy, and we have there's a telescope, and there's a team doing data analysis and astronomy. Also, apart of that, we have a big team in UWA doing physics education for schools, and we have program like a quantum girls to encourage female participants in STEM. We teach school students and start early. Excuse me. So the Jingjing Gravity Precinct, we have our research facility in. And nearby, we have a Gravity Discovery Center we are affiliated with. And then we also have this telescope. In the high optical power facility, basically, that's what inside the facility look like. Although we have only 80 meters, compared with LIGO, Virgo, or Kagra, they're kilometers. They were sort of a baby. We cannot be a detector to detect gravitational waves, but we use that to develop a technology. We have all the necessary components. We have high vacuum, we have suspended optics, and importantly, we have very high power. And although our test mass is not 40 kilometers, but our power, laser power to the mass ratio is similar with advanced LIGO. So we can do lots of research. Also, because I think we are the only one with similar power, and we can research on lots of high power related issues. First, with high power, although the mirror is very, very good material, but a teeny bit of absorption, it's with kilowatts, megawatts laser will still make the mirror hot and deformed. We call the thermal lensing. And also there's other thing we call parametric instability. That means that because the laser, we know that we have the optical, pressure, radiation pressure, that it actually interacting with the mirror, so that it can make mirror, excite the mirror motion, and the mirror start to ring. And that make you can't increase power. You increase the power and the mirror start to ring. So in UWA, we develop technologies so that to suppress parametric instability, which is one of the main contribution for us from UWA to the first detection of gravitational waves. Of course, with such a system, we still need advanced control system, and we need large seismic arrays to monitor the ground motion to make our system working better. So I'm just flash a few pictures. We soon will have a large kilometer seismic array to monitor the ground motion, and also that's basically to improve low frequency. We just reduce the low frequency noise, and also we have high power to experimental to compensate the thermal compensation of the test mass to reduce the to suppress the parametric instability. And we have rotating sensor to basically combined with the seismic array to better reduce the low frequency vibration noise and also the Newtonian noise. We also have a research into test mass materials, and this is some birefringence, because I don't know how many people know what is birefringence. Basically, the polarity of the laser light changes with the materials birefringence. So we have developed a technique to testing different type of birefringence. Also, in this in UWA, in the lab, in the UWA campus, we develop technology using the micro resonators, optomechanical interactions, basically a cavity with some tiny little bit of a, you can see the scale, very little resonators, and through optomechanical interactions, we could develop technology to beat the quantum limit. Some people would say, okay, quantum limit is the ultimate limit. The squeezing is one of ways to sort of, when I say beating the quantum limit, and also what we develop, we try to make the quantum limit, beating the quantum limit in a wide frequency range. It's very challenging, but the work is very rewarding. So into the future, I want to say that we still hoping that we'll have Australian detector. And when I say, you can see from here, without me say too much, you can see Australia, adding LIGO-India, we have this triangle, better triangle, then you can better sky localization of the source. And with the Australia detector, you can see this triangle is very, very big. And with that the source, gravitational resource could be almost pinpoint where it is. And that will help with multi-messenger astronomy. Basically, the optical telescope can quickly turn into the source you identified and to find more, because gravitational wave is what I would say one spectrum of the astronomy, but then from the other spectrum, then the optical telescopes will quickly join the search and will get more information. And so for us to get into this is probably well-known spectrum. And for us to Australian detector, we're hoping to at least in the future, either high frequency, we can dig into the high frequency. This is a LIGO, hope for LIGO Plus or like or A sharp. It's in this range, and we'll dig into high frequency, or we have a good detector that join the future detector range with our more broadband sensitivity improvement. And also just finally, I just want to say Australia-Indian collaboration has a long history. And Achina sort of point out that the first one, Sanjeev and Bala, that I know them both very well, that we had, they visited here a long time ago. We collaborating with gravitational wave or astronomy. And then later on, we have many exchange scientists and students, and we have a PhD student doing in Australia and UWA, and they came back, and then they came back and joined LIGO-India. And so with LIGO-India, we provide, it will have more motivational opportunities for exchange with Australia. And I would say we welcome all the motivated students to join Australian research. And you can contact individual researchers. Ausgrad has a profile in their webpage. If you have interest in certain area, you can contact them. And there are lots of scholarships. High-performing students can do PhD with different universities. And also there's quite a lot of Australian Indian special programs that you can seek, so that we can have this short-term visiting or even longer-term study in Australia. I think with that, I'll finish from here. Thank you.
Thank you, Professor Lee, for this very inspiring talk. Yeah, good to, and it was eye-opening for me as well how much Australian community is doing for detector development and sensitivity improvement. So we have time for one question, and there is one on the chat from Vasudha. So they are saying that why was AIGO not prioritized more, considering it would have provided a larger baseline and improved detection localization to a huge extent? Was there any particular scientific problem?
Why not prioritize more? Funding, I suppose. And Australia probably not as bold as India. And we lost, I think people probably hear about before LIGO-India, there's a proposal LIGO-Australia. But we sort of lost of opportunity for LIGO-Australia. But, for LIGO-India, of course, that there's opportunities for, we would, will help, happy to help. And it's basically, I would say, the funding. And we Australian researchers, we have a long history, we have the expertise, but
Yeah, that makes sense. Yeah, thank you. Thank you, Professor Lee, for this talk and being part of the symposium. We very much appreciate your time.
Thank you.
We thank again Professor Lee for this very nice, very wonderful overview of contributions from Ausgrad, highlighting also the early career researchers in the collaboration, their contribution, and also talking about outreach, because Ausgrad is doing wonderful work in encouraging female participation in STEM. So thank you very much again, Professor Lee. And so now we would like to move on to our following speaker. She's Professor Isabel Cordero Carrion from University of Valencia in Spain. And she will tell us about, particularly about Virgo scientific collaboration. Isabel, can you share screen? And I love the title, Virgo collaboration, women also do science. Exactly.
Thank you very much. I think you can see the slides and my mouse and everything, and you can hear me well. Yes. First of all, I want to say I love the title. Now, every time I see GW, I will think first about glorious women and then about gravitational wave. I love the new acronym. And also, I want to say huge thanks to Professors Devarati Chatterjee and Professor Aurana Gupta. I was not able to pronounce the name properly, sorry, but you are doing amazing work, and I really want to say thank you for organizing this. Huge thank you for letting me speak a little, and thank you for all the work you do in order to get confidence and support to women and to people in general to do science to have a critical thinking, and to work together, because we are in some times where we think that isolated person can do great things, but we are not really aware that when you join wonderful people, you can do really, really wonderful job. And it's really nice and really satisfactory to be part of these great collaborations. So this is my first message. Now I will try to say a few things and not repeating the wonderful messages given by the previous speakers, and that I am pretty sure that next speakers will do also a great job. First of all, what we are trying to do is just fascinating. I mean, the current interferometers are using light to detect perturbations of space-time itself. So the place where you are, not what you are, but the place where you are is vibrating. That's fascinating by itself. And moreover, we are challenging this goal of detecting these perturbations. We were able to do it. So, and I say we because it was really, really a joint work of a lot of people during a lot of decades and from very, very different aspects. So the problem we are facing is just amazing. So let's try to enjoy it a little. I think that's very important to give the message that what we do is fascinating, is challenging, but it's really cool. And then it's not a question of one person. It's not a question of one discipline. You need a lot of things. You need, first of all, mathematics, geometry, analysis, equations to understand what is the theory behind all this story. It took a while just to understand what was the meaning of general relativity. Then we understood that this gravitational wave was not an artificial mathematical effect. It was something inside the equations. It was a very nice surprise that came with the new theory. And then it took also a lot of time to understand if we can really trust the equations, if the equations have nice mathematical properties, if we can solve the equations numerically. It was really hard, but we managed to do that. You need a lot of physics. You need to understand if the universe is following this wonderful theory. If you have a solid physics principle behind all these equations, if you can really couple these equations of gravity with other interactions in nature and how they talk each other. And this is something really, really amazing too. But that's like the mathematics, the physics. Let's go to the real world and let's try to detect what you are studying in a paper, in a computer, in a book. And then we need engineers. We need people analyzing optics, mechanics, and frequencies of a lot of instruments and elements of the instrument. So you are really wonderful if you can help us with the shot noise, with the seismic noise, and with all the kind of noises that we know and a few ones that we have no idea that are affecting or the data that we need to understand in order to extract the signals. And then we have these people doing this data analysis. Once the mathematics, the physics, and the engineer did a wonderful job, what we can extract, what we can detect, is the signal that we are observing the one we were expecting? Do we have something new? Can we understand the origin of the astrophysical scenario that is providing these signals? Do we have some degenerations between several parameters? I mean, that's by itself also amazing. And at the end, everything we do, we want to give all this information to the people, to the society, to the community, because most of the people working in all these areas are in public or private universities with a lot of support from society itself. So it's really like the last but also very nice element in the chain when you say, yes, we have detected gravitational waves. And I really want to say, we need every single thing with a lot of details and a lot of difficulties and a lot of challenges But there were a lot of people behind in order to overcome all these barriers and all these problems in order to get signals, real signals of the space-time vibrating. I am not sure if I really transmit what I feel, but I am so happy just to be part of this history and this collective history. As you have seen, this is not coming from one continent. This is a worldwide effort, and you have people working in USA, in Europe, in Asia, in Australia, Oceania. It's really everyone. We need everyone, and we need all the contributors, all the contributions. We are also celebrating the 10th anniversary of the first direct gravitational wave detection. Before this direct detection, we had enough information, let's say in this way. We were pretty sure that gravitational waves exist. We had the pulsar orbital pulsar decay, and we had a lot of information. And also we had the equations themselves telling us in our computers, this should be real. You need to look for these signals. But 10 years ago, we were saying to the world, we have a detection in the observatories. The work is done by a lot of people, and we don't have only one single detection. You showed some previous plots before. We have now a catalog of hundreds of detections. It's a collective work during decades, and I want to say I was so lucky to be part of the Virgo collaboration since 2016. And I am really living the wonderful, the gold time of gravitational wave astronomy. But I have to say thank you to a lot of people that allow me to start working in this field in this wonderful moment. So just let me say a few numbers of the collaboration, of the Virgo collaboration. These two detectors are the LIGO detectors in USA. This is the Virgo detector in Italy, and this is the project of the Cagra detector that is also part of the network. We also mentioned, we also listen about LIGO-India, Australia, GEO, and there are more and more efforts. And there are a lot of technologies that are developed in smaller observatories that then comes to the bigger instruments. So it's really a collective story, an effort, and congratulations. But let me just say a few words about my detector, my collaboration, just to give you a few numbers. The Virgo collaboration is funded by the French National Center for Scientific Research, CNRS, in France, and also the Italian National Institute of Nuclear Physics, IFNN, and also by the National Institute for Subatomic Physics, NICEF, in Netherlands. But these are the funding agencies. But if you take into account all the people working in the Virgo collaboration, we are more than 1,000 members in the collaboration, representing 175 institutions in 21 different countries. Most of the countries are in Europe, but we also have colleagues and research groups outside of Europe. And that's not the story. I really like to talk about this collective effort because there are a lot of things done in a coordinated way between LIGO, Virgo, Cagra collaborations, and even more people outside our collaborations. But this is done by people. So why don't we show a few faces? And by the way, why don't we show a few female faces? Because sometimes, in general, I think the contributions done by women in science were not given the proper visibility. We were not working in the proper conditions. And even if we, let's say, overcome all these problems, our work was not sometimes even with our names, was given to other male colleagues. So I am just going to select a few among all these 1,000 people that we are in the Virgo collaboration. I'm going to select a few people, and I really want to show her faces, her stories, And a few comments I really want to give to everyone, but in particular to young generations, because you are really the future. We need great science, but we can do science in a better way. We can treat people in a better way, with more visibility to the young people doing a lot of work that sometimes are not recognized properly, for example. Well, first I'm going to start by myself, because I have started to talk about the collaboration, all this amazing science, but what I do. So I am professor in applied mathematics and computational astrophysics. I did mathematics and then I did a PhD in astrophysics. So first thing, there are a lot of different ways where you can contribute to this wonderful science. I am also in the last part of this change, and I do a lot of outreach and scientific communication. And I really want to say, in particular, LIGO-India and OSCRAF, you are doing amazing outreach and communication work. And I hope that your society really recognize all this effort, and thank you, because it's really important. When I enter into the Virgo collaboration, basically you need to fill in a classical formula. So you put your affiliation, your name, email, blah, blah, blah. And then you need to put if you are permanent or not. I have a lot of teaching duties, so I do my best. And also you need to put like a specific area, no? So you had, we had physicists, engineers, technicians, informatics, but there was no mathematician. So I asked, the first thing basically I did when I entered into the Virgo collaboration was to say, hey, sorry, you forgot people in mathematics. So it doesn't matter. I know it can be a little hard if you are the first one doing something in a different way. But it just means that. It means that maybe you will be the first one, but it does not mean you will be the only one. And it does not mean it is not important. So don't be afraid to do things in a different way, in a respectful way, but in a different way. Or don't be afraid to be the first one. I'm pretty sure that if you look good enough for any other person with your profile, you will find more people. So since I am part of the Virgo collaboration, you can be mathematician and you can also be part of the collaboration. I do a lot of outreach and communication because I really think we need to engage society as a whole. It's not only about the gravitational wave, science, it's more about the scientific and critical thinking, and it's also about our future. If your country has more support into science and research, your country will be better for everyone, and that's really important. I don't want to talk about me because, I mean, you can really write me. This is my email, and you can write me at any time. I love listen people. I love listen young people because you do have wonderful ideas. But I really want to say thank you to other people in my collaboration that allow me to say a few words. So first, I want to say thank you to Paola Leacci. She's associate professor in Rome, in Italy, in La Sapienza University. And her research focuses on gravitational wave data analysis. One of the points that we have already listened about. She has been a member of the LIGO scientific collaboration since 2008, and she also had important responsibilities in the collaboration. She was chair of the Virgo Continuous Gravitational Wave Working Group and also co-chair of the joint LIGO Virgo Continuous Gravitational Wave Working Group. She works in continuous gravitational wave data analysis, including the development of robust and novel methodologies for the detection of this kind of sources. This is a kind of source that we don't have a signal yet, but it's a let's say a candidate, a strong candidate to be one of the new kind of signals we can observe in our current or near future gravitational wave detectors. I also want to say thank you to Melissa Lopez Portilla. She's a postdoctoral researcher in Netherlands, in the Utrecht University and IKEF Institute. Her research focuses on machine learning and gravitational wave data analysis, and she's really young. She just became doctor very recently, but she has already been responsible of the machine learning group. She was part of the early career representative in the Virgo steering committee, and she's member of the generative AI artificial intelligence task force. She has already supervised bachelor students, master students, and predoctoral researchers. And for example, you can check about this gravitational wave learn series, where you can learn about gravitational wave data analysis techniques. She received the Impact Award in Data Science by the American Physics Society. And I love this picture because this is a very recent picture. She was pregnant, 6 months pregnant, during a visit to the Virgo Observatory. And now her daughter is less than 1 year, and she's still smiling a lot, like in this picture. I just want to say one thing. It is fully okay if you don't want to be mother. It is fully okay if you want to be mother. It is fully okay if you want to be a young mother. And it is fully okay if you want to be a not so young mother. My daughter has less than 2 years, and I am a very happy mother with a very happy father next to me that is promoting my science and my family role, my family roles. You can be a great person, a great scientist, a great mother, or you can decide not to be mother, and it's fully okay. What we can do is to respect all decisions, support and facilitate the conciliation between family, private and professional balance. And this is something that affects everyone. We may decide not to be father or mother, but we have parents, we have family, we have friends, and we have the right to have a good balance between our work and our personal life. It is not acceptable at all to judge or to put barriers or to don't understand that people can have different decisions. If we are more diverse, we will face in a better way the problems that we need to solve. And we have huge problems to solve. So I am very happy that Melissa allowed to show this picture. And the group picture of my group was done when I was super pregnant. And I am also very happy that I was in this picture. And we need to do things in a different way because we need everyone, and we need everyone in a happy mode. I also want to say thank you to Barbara Garaventa. She's postdoctoral researcher, very young, brilliant woman in Italy, in the INFN Genova Institute. She's a member of the Virgo collaboration and also of Einstein Telescope. We have also listened about the future experiments that we are thinking and designing in order to continue this wonderful science. Barbara's research activity focuses on quantum noise reduction techniques and magnetic noise mitigation for gravitational wave detectors. So she's working in the experimentalist area, and we also mention about this quantum noise reduction and squeezing techniques. She's member of the quantum noise reduction group, and she has contributed to the development and operation of squeezing subsystems. And we also listen how important these techniques are for current and future interferometers. She's actively involved in a squeezing experiment in the context of Einstein Telescope research and development areas. And this is an alternative frequency-dependent squeezing method to filter cavities. Within the Einstein Telescope collaboration, she's coordinator of Magnetic Noise Reduction Working Group, and this is not independent, so future collaborations are also taking advantage of the knowledge that we have in current collaborations. So she's working in close collaboration with the Virgo Magnetic Noise team to address magnetic coupling and mitigation strategies for future underground interferometers. And I want to finish with Alexandra Eleni Koloniari. She's predoctoral, she's even younger, predoctoral researcher in Greece, in the Aristotle University of Thessaloniki. And she works on gravitational wave data analysis using machine learning, neural networks for large-scale multi-detector searches. She's the leading developer of Ares gravitational wave. It's a pipeline alternative to classical gravitational wave search algorithms. For example, these machine learning, match filtering techniques that we also mentioned, we also listen. And she has served as a catalog duty manager, acting as a rapid response team responder. She has participated in reviewing tasks and in outreach activities. And she wants to aim to advance artificial intelligence-driven approaches in gravitational wave astronomy to contribute for the future development of data analysis methods for current and next generation detector networks. I want to finish with two fast comments. The first one is that you may not know, or maybe you know, and then I will be very happy. This woman, she's a French physicist and mathematician. She's called Yvonne Choquet-Bruhat. And if you don't know her, we have a problem, because she's a key figure in the understanding of the theory of general relativity. We know that general relativity has local solutions, global solutions, stability properties, and that gravitational waves is a real thing and not a mathematical artificial element, because in a great part, because of the works of Madame Choquet-Bruhat. No insignificant science contributions from women only enriches our collective memory. We need the contributions of everyone, of the past, the current, and the future people, including women. Yvonne sadly passed away 1 year ago. She decides, I don't know, it's a way of saying, she died on 11 February 2025, with 101 years old. And you know that 11 February is the International Day of Women and Girls in Science. So now you can celebrate that day. You can celebrate anniversary of gravitational wave direct gravitational wave detection, anniversary of Yvonne Choquet-Bruhat pass away, and also the International Day of Women and Girls in Science. So we have a lot of things to celebrate in 11 February. And actually, I start doing a lot of things and activities that day, and I finished more or less this week with the International Women's Day. When the Eiffel Tower was constructed, only 72 names of male French scientists were written in this construction. Very, very recently, the mayor of Paris decided that Yvonne Choquet-Bruhat name, Cécile de Witt-Moret name, and other 70 female French scientific women names will also be added in the Eiffel Tower. I think this means that the Eiffel Tower will be brighter once we have these names there. And it's very important, these activities. If you don't know Yvonne Choquet-Bruhat, go to the Wikipedia, go to internet. And if you don't know Eminator, this picture is from Eminator. It's an opportunity. These activities are an opportunity to give visibility to amazing work done and doing and be done by women. So thank you very much. I hope this will inspire new people. I hope that in next editions, I will be clapping for the wonderful talks of young women that enrich our great science. Thank you very much.
Thank you for the
Thank you so
wonderful
much.
talk, Isa.
Yeah, thank you so much. Yeah, it's very inspiring, and I'm sure the audience are also feel inspired from that. Please write your questions in the chat if you have a question for Isabel. Maybe just for if we want to ask, I can ask one question is about what will be the opportunities for young students who want to enter the field in Europe or in Virgo collaboration. If you can mention some of the things briefly.
Well, first of all, don't be afraid. It took me around 1 year to understand more or less how the collaboration works. So that's challenging, okay? And it's not because you are young, it's just because we are a lot of people. And it's hard to coordinate 1,000 people and a few thousand people around the world. But don't be afraid. We do need people, and we need people willing to work. So just start with a small thing. Contact with a person that you trust. It doesn't matter if it is in your group or in another group. Just contact that person and say, I have time and I want to contribute. What I can do? And you will start maybe with something small. But I can tell you that the person that is in charge of aligning the light in the Virgo Observatory finished her PhD while doing that. So it doesn't matter if you are senior, it doesn't matter if you are a early career researcher. Just start with something small. Be willing to work a lot. Be open to listen people. Be open to make mistakes, but understand why you have done those mistakes. And then enjoy the moment. It's really amazing to be part of this group. If you're not enjoying the moment, try another thing. Try to talk to another person, try to contribute in another project, and try to have a network of people supporting and valuing your work. That's very important.
Yeah, thank you. Yeah, that's very assuring. Yeah, I think for young students, this will be motivating to do the hard work, and I think you will be there where you want to be. With
And
that, I
yes,
think
just one comment. There are a question. There is a question in the
Yeah,
chat.
there
There
are
are
a couple of
wonderful
questions.
introductory books, recent and also more classical books. In particular, you can take Yvonne Choquet-Bruhat's book. That's wonderful. And also there are other more recent books about general relativity. And you always can go to your university, knock the door of your professor and say, hey, do you have some time for a chat? We are more open than some young people think. And I am pretty sure that most of the people connected here, senior professors, will be very happy to receive you. Thank you very much.
Thank you very much, Isa. I see some questions in the chat. I think these are from young students who want to join the collaboration and want to know more about it. So I just want to mention that we have a separate interaction session tomorrow from 7:30 p.m. Indian Standard Time. So you can learn more about, career paths and career guidance from early career researchers. So try to be there tomorrow if you can ask them directly. So thank you very much again, Isa, for this wonderful talk, guiding us through the Virgo collaboration, contributions from women. It was very enriching to know about contributions from women across Europe and other places. So let's move on to our next speaker. So Andrea Monica is here. So our next speaker is Andrea Monica Scotta. She's from Institute of Space Sciences, Romania. Are you able to share your screen, Monica?
Yes, of course. Can you hear me?
Yes.
Okay. And now, can you see my screen?
Yes, now we can see it.
Okay.
Yeah, you may go ahead.
Okay. So, hello everyone. My name is Andrea Monica Scorza. I am a scientific research assistant at the Institute of Space Science in Romania. And today I'm going to talk about the LISA mission, LISA consortium, and women scientists' involvement in this mission. So something quick about me. So I've graduated the Faculty of Aerospace Engineering, both in bachelor's and master's degrees. And I've had some preparation, some training done at the European Space Agency. Afterwards, I've just embarked, actually, last year, the new group, the Astrophysics, Space Exploration, and Quantum Computing Group here in Romania. So with it, the LISA mission. I'm part of the data distributed processing centers. center here in Romania, part of the system team here. I'm working a bit in the product assurance, quality assurance group for the LISA mission. I am a core member of the LISA Monday Call organizing team, and afterwards I'm involved too in the early career scientist group and instrument simulation working group in the LISA consortium. And I've just started my PhD actually in automatic control and computer science here in Bucharest. So LISA mission is an international effort involving the European Space Agency, its member states, the LISA Consortium, and NASA. It features 3 spacecrafts that are arranged in a near equilateral triangle, and they will be exchanging laser beams across 2.5 million kilometers arms. So with this, the precision laser interferometry, LISA will be able to compare the test masses separations that are shielded from the disturbances from the spacecraft, and this will enable the measurement of space-time strains over time. So we have different sources that emit in different gravitational wave frequency bands. The millihertz band, it's in between the LIGO, Virgo, and the pulsar timing arrays band, and it's richly populated with strong sources, but it's yet unexplored, and this will be unlocked by the LISA mission. So LISA will try to achieve its goal of 4.5 years baseline operation, extendable to 10 years. Like I said, it's a mission led by ESA, NASA, and the international partners that provide the technologies, the telescope itself, the test masses, and so on and so forth. Okay. So the LISA mission as we know it today has its concept studies tracking back to activities that had been undergone in the Joint Institute of Laboratory Astrophysics in the USA in 1970s. In the early 1990s, LISA was proposed to ESA as a mission by the LISA Consortium. And the current formation of the 3 spacecraft was agreed upon in 1998. And then the study team of the ESA's Fundamental Physics Advisory Group recommended to carry out LISA in collaboration with NASA. But it was not until 2015 that the LIGO-Virgo collaboration made the groundbreaking discovery that we know about, the first gravitational wave, and paved the way for a new era in this science. So now we find ourselves in the implementation phase after the adoption that was in 2024. And of course, here I specified that we have some knowledge that the concept of low frequency gravitational wave detection is possible through the successful mission called LISA Pathfinder. LISA has some scientific goals like for tackling key astrophysics, fundamental physics, and cosmology questions from the ESA's cosmic vision. So we have some highlights like detecting the massive black hole binaries, mergers, capturing extreme mass radiation spirals, hunting the stochastic background for early universe events, and these translate into the production of the vast amount of data that needs processing. So this storing and analyzing of this data, it's a task that will require and requires the development of data analysis pipelines and the construction of data processing centers. So we have the so-called ground-based data processing pipelines that transform raw spacecraft telemetry into scientific insights through a structured that flows from L0 level data to L3 data products. So we have in the L0 data product the multiplex time ordered telemetry, which is processed at ESA. And then it's noise clean and it leads to L1, which afterwards will feed the global feed at the EU-led distributed data processing center. And we will get the L2 outputs, which are the probability density functions and reconstructed waveforms from the sources. And this will culminate with the L3 catalog of gravitational wave source candidates. And this will include detection confidence, astrophysical parameters, and strain time series. We have LISA consortium, which is an open community-driven group that proposed LISA as the ESA's Cosmic Vision L3 mission, like I've said before. And this united all the science experts from all the member states and the US for this endeavor. We have, after the post-mission adoption, the LISA consortium adapted to the European Space Agency's new LISA science team, so-called LISA science team. And it stayed in the community as an open hub with science interest groups that complement the LISA science team and pathways for early career researchers and public outreach on LISA science, but also serves as an expertise pool for science, ground segment implementation and performance and operation, fostering close ties with the LISA science team. We have individual members in the LISA consortium that can be core members. So core members are the one who commit to specific deliverables, subjected to regular reviews, and can opt into author lists for consortium papers. And they primarily work in the so-called working groups. Afterwards, we have the community members, which are members that are informed are informed of the evolution of the mission of the consortium itself, but do not have to commit to deliverables, and they do not join the member groups of the working groups. We have the consortium work areas and the organization of the LISA consortium. So we have decision and policy group, management and strategy group, and implementation of the council's decisions group. So we have core members that are represented in the consortium council. The council is the highest decision body of the consortium. So we have decisions of the consortium enacted by the management team. We have the spokesperson of the LISA consortium, the LISA science team representative, and the scientific working groups that I've specified about that work directly for the consortium deliverables. In the And here uh, in the organization of the LISA consortium, we have women that are regularly elected to leadership roles in the working group co-chairs, past and present. And also we have a diversity, equity, and inclusion committee that supports diversity in decision-making of the consortium. For an example, as an example, I can provide you this, that the appointments and election committee can hold calls for appointment to committees and working groups co-chairs elections. And the Diversity, Equity, and Inclusion Committee can actually ask the Appointments and Election Committee to hold the call open for as longer as the pool of applicants are sufficiently diverse. LISA consortium is comprised of 23 countries. Here it's for the consortium council, number of people involved in LISA consortium. And we have in the LISA consortium council 21.5% women. And I would like to actually pinpoint towards that those women that actually take part to the LISA consortium path to reach the desired output of the LISA mission. So we have firstly Ana Caramete, which is also my coordinator here in this Institute of Space Sciences and who supported me along my career as well. So Ana is the deputy of the PAQA core team. She is the Romanian representative of the Distributed Computing Center. She's part of the Low Latency Alerts Coordination Unit, where her main contribution is with the development of AI-based low latency pipelines for fast processing and characterization of signal detected by LISA. Before, she was involved in Euclid mission, Proba3 mission too, and she has a PhD in the context of the Blank mission. And as hobbies, she's involved in mentorship activities organized by the Association of Women in Engineering, Science and Technology. And thus she's inspiring and helping women in Romania and not only to pursue their STEM careers. Also, I would like to share Devnandini Mukherjee profile because she is a successful postdoc at the University of Birmingham. She's working in gravitational wave data analysis and searches for massive black holes. She is developing, she's contributing to the global fit of the overlapping gravitational wave sources. And as hobbies, she likes to listen to audio stories, podcasts. She likes to paint, to write stories, poetry. She likes photography. I'm sharing with you this because this was actually and is actually an initiative of the LISA Consortium Communication and Implementation Working Group to share the stories of people that are involved in the LISA Consortium with the wider public. And this initiative is also called the Humans of LISA. Also, I would like to specify that you can keep yourself up to date with the news from the LISA Consortium by accessing the LISA Mission website, subscribing to the LISA Consortium newsletter, which actually was successfully delivered earlier this week. And you have a frequently asked question page in the same in the LISA Mission webpage. And I would like to present the other part of my team in Romania. So we have Maria here. She's a PhD student at the University of Bucharest. Her work is centered on quantum computing algorithms for space missions and space applications with a focus on quantum neural networks. We have Florentina here, and she is a PhD student at the University of Bucharest as well, and she develops multi-messenger studies, MBHB catalogs, and she's simulating gravitational waves for parameter estimation studies. And she's also the LISA Early Career Scientist co-chair. We have Alice here. She actually obtained her PhD title earlier last year, and she's a member of the KM3Net collaboration tool, with her research focusing on analyzing the sensitivity of the detector, optimizing it for nuclearides, and she also studies exotic scenarios of black holes growth. And we would like, through this manner, to give you some greetings from Romania, from the team here that is working for the LISA mission inside the LISA consortium, and in this way encourage everyone that want to take part of this consortium to search information on how they can actually apply for a position there, because there is a page where you can actually um, that you can actually access for entering the LISA consortium, and you find there some quick guides that can help you with more details on the sign up, on the pledges, on the member groups, projects, and so on and so forth. And with this, I would like to thank you, and I would be glad to help you with any questions that you might have.
Yeah, thank you so much, Monica, for this information on LISA consortium and LISA opportunities. So yeah, please write your questions on the chat for Monica, and we will read to her. So maybe in the meantime, I can ask Monica. So can you tell us, like, what is the need currently the LISA consortium have in terms of person power? Like, where do you think will help in the future if people focus on, say, instrumentation or data analysis or something? So can you tell us more about that? Where currently there is a most need in a field in LISA?
Okay, so yes, in the LISA consortium, like I've said, there are different working groups that are working in different areas. Mainly in the instrument simulation, from what I know, it's now part of ESA's tasks, and the main contribution from this side. But for the others, I mean, given the restructuring or a bit of the channels that we are communicating, actually, now people are gathering and are finding out what they can do by being present in the LISA Monday call. That is a meeting that we have each Monday for keeping up with the information that it's spreading inside the LISA consortium, keeping up with the projects that are inside the LISA consortium, because different working groups have different projects and you can apply to those projects if you're interested, if you believe that you can actually contribute to that project. So mainly it's like that, that either you are a member of a working group, either you want to become a member of a working group because you find an interesting project that they are working on there and you want to contribute to. Mainly, this is how you find out what is needed, what is it, what are the things that are ongoing right now.
Yeah, thank you. Yeah, that's very useful. so as Professor Lee said that students mainly kind of gravitate towards more of data analysis and data science, and there are less people who are more interested in doing actual instrumentation or laser or experimental work. So is this also the LISA consortium is facing, because that's true for ground-based detectors. So for, I think since it is done by ESA and NASA, I think you may not feel that kind of a deficiency in person power for working on instrumentation.
Let's thank Monica once again for this very nice overview of the LISA consortium and also the different DEI initiatives. Thank you very much, Monica. Also,
And I think you too.
yeah, you're welcome. And also, if anybody else has any questions for also the previous speakers, you can put it on the chat. Maybe if the speakers are around, they can already answer that. Okay. So, all right. So let's move on. So we have with us Professor Maura McLaughlin, who is our final speaker of this plenary session. Professor McLaughlin is from West Virginia University, and she is going to tell us about the International Pulsar Timing Array. Maura, are you able to share screen?
Hey there. It's really great to be here. It's great to see so many people and especially so many women on the call. Let's see. How does that look?
We can see your screen. It's not full screen though. Yeah, now it is.
Okay, great. Okay, cool. So I have a half an hour, right? And I'll try to keep the talk to like 25 minutes so we have some time for questions.
That would be great.
I'm just looking at my watch. Okay, great. Yeah, so again, thanks so much for having me speak. I'm going to talk about pulsar timing and detecting gravitational waves, and in particular, try to focus on the efforts of the International Pulsar Timing Array. So a little bit of introduction about the IPTA. So the IPTA is a consortium. It was founded in 2009. It includes regional collaborations in North America, Europe, Australia, India, and South Africa, and hopefully soon China, from institutions in about 12 countries. And you can see this map here. It's comprised of Nanograv in North America, the EPTA in Europe, the MPTA or South African PTA in South Africa, the Indian PTA, and the PPTA, the Parkes Pulsar Timing Array in Australia, and a Chinese Pulsar Timing Array collaboration is also in the process of joining. If you're interested in what I'm talking about, we have a meeting in South Africa in June 2026, and there's a student workshop for the first week of the meeting, so you would be very welcome to attend that meeting and learn more. So I'm going to start with an animation that shows sort of like the big picture of what we're trying to do. So we are timing pulsars. These pulsars are all in the Milky Way galaxy. And we basically have constructed like a giant gravitational wave detector where the arms of the detector are the paths between the Earth and each of the pulsars in this network. And so when a gravitational wave passes through this network of pulsars, it stretches and squeezes the arms. Just like LIGO arms are stretched and squeezed by gravitational waves, the same thing happens with this pulsar network. And we are trying to detect this stretching and squeezing by measuring the arrival times of the pulsars in the array very, very precisely. And so that is the big picture of our experiment. Very quickly, pulsars are rapidly rotating neutron stars. All the work that I'm going to be describing is done with radio telescopes. We use a special kind of pulsar, millisecond pulsars. These have the shortest periods. There's about 500 of these millisecond pulsars known in our galaxy right now. You'll see as I get through the talk, though, we only use about 100-ish of those for pulsar timing. Some of them are just too far away, too messy timers. But for the 100-ish or so that we can time well, we can measure their pulse times of arrival to something like hundreds of nanosecond precision, and in some cases, even better. So they are cosmic clocks. And every time the beam of one of these rotating neutron stars passes our line of sight, we measure a pulse, and we can time these pulses and then look for the deviations expected due to gravitational waves. So this is the very special signature that we're looking for in our data. As we know, gravitational waves perturb in a quadrupolar way. So if two pulsars are in the same direction, we expect them to have correlated perturbations. So if a pulse from one of those pulsars arrives late, a pulse from another pulsar in that same direction should also arrive late. If they're separated by 90 degrees, we expect anti-correlated perturbations. If they're separated by 180 degrees, we expect a correlation in those arrival times again. And when you do the math and average over an isotropic distribution of sources and pulsars, you get this Hellings and Downs curve. So this shows the correlation we expect between arrival times versus pulsar angular separation. So you can see this basic quadrupolar signature, positive correlation at 0 degrees, negative at about 90 degrees, and positive again at 180. So the name of the game is timing a whole bunch of pulsars distributed across the sky, and then cross-correlating their arrival times to look for this very special signature versus angular separation, which tells us that these deviations are due to gravitational waves and not due to something else. One kind of cool thing about this experiment is that when we measure this correlation, we're actually measuring the effects of gravitational waves on the Earth itself. The pulsars are all at different distances. They are in different gravitational wave environments. The Earth is the only sort of like correlated signature in the data. So we're actually like seeing the effects of gravitational waves on the Earth. And this is a prediction for a stochastic background of gravitational waves. So this Hellings and Downs correlation is assuming like an isotropic distribution of gravitational wave sources. And you get similar correlations for single sources, but this specific prediction right here, this Hellings and Downs, is for a background of sources. Okay, so just to put us in context with other experiments, this shows characteristic strain versus gravitational wave frequency. And so pulsar timing array experiments are sensitive to very low gravitational wave frequencies. So 10 to the minus 8, 10 to the minus 9 hertz. And that's because the time scales of our experiments are long. They are decades long. We don't get to the low strain sensitivities that LIGO does or that LISA will. But fortunately, there are extremely massive binaries at the cores of merging galaxies that have very high strains that are within our sensitivity range. And you can come up with like a rough metric for what our sensitivity is by looking at the precision with which we can time pulsars, which is typically like a couple hundred nanoseconds over the time scale of the experiment. And that's about like 10 to the minus 15 in strain. So this stochastic background, that's our primary source for detection right now, at least, has a red spectrum. So there are more binaries at the lower gravitational wave frequencies contributing because they take a longer time to move through the low frequency parts of the band than the high frequency parts of the band. As with LIGO and LISA, we're sensitive to a stochastic background, so the sum of all the gravitational wave sources in the universe emitting in this frequency range, and also individual supermassive black hole binaries. This shows example sensitivity curves. These are for the nanograph collaboration that I'm a part of, but each PTA will have a very similar sensitivity curve. And the sensitivity peaks at 1 over the time span of our observations. So with time, our sensitivity will move kind of leftward in this plot. So we'll get like more and more sensitive to low frequency signals. And of course, our sensitivity also increases with time. This little spike here is because we're not sensitive to periods of 1 over a year, because we would fit those out in our pulsar timing models. Okay, so I'm going to talk to you a little bit about pulsar timing and then tell you a bit about the recent results and the future of IPTA science. So pulsar timing is super fun. I've been doing this for decades now, and every pulsar is a little puzzle. We measure arrival times, and then we need to fit them to a model that predicts like when the next pulse will arrive or when a pulse a month from now will arrive. And there's lots of things that affect those arrival times. Obviously, the pulsar spin period, the pulsar period derivative, Most of our pulsars are in binary systems with white dwarf stars, so we need to account for the orbits. The interstellar medium is not empty. It imparts frequency-dependent delays. These delays vary with time, so we need to fit for a dispersion measure and dispersion measure variations. Of course, the Earth is moving around the sun, so that's going to affect the apparent arrival times of the pulses, so we need to correct for that effect. Because of that, we're also sensitive to pulsar position, proper motion, parallax. We can even probe the solar electron density when our line of sight travels close to the sun. So we construct these timing models based on many, many years of pulsar timing data. I'm going to just talk a little bit about the collaboration that I'm part of, like our observational scheme, but all of these collaborations in the IPTA kind of have similar schemes. So in general, we put out discrete data sets. So we put out a 15-year data set a few years ago. We're working on a 20-year data set right now. This plot here, these are pulsars on this axis and time on this axis. The colors are different frequency telescope combinations, but you can see with time we're adding more and more pulsars to the array. So pulsar searches are really important. The different colors are different radio frequencies. And so the one like really important thing is to fit for these interstellar medium effects. We need observations at multiple frequencies. So that's why for most pulsars, you see at least like 2 different colors. Yeah, so we are currently timing about 70 MSPs. The 20-year data set will have about 78 MSPs observed with the Green Bank Telescope in West Virginia, Arecibo, CHIME in Canada, and the Very Large Array. And we do observations roughly monthly with the GBT Arecibo and the VLA, and daily with CHIME. And this is a really similar observational scheme used by most of the pulsar timing array collaborations. Each PTA puts out data releases every few years. They'll include times of arrival for the pulsars, timing models, which look something like this. So all of the different parameters that we model these times of arrival with. So for instance, for this pulsar, we have spin frequency, orbital period, binary parameters because it's in a binary, etc. So you can download these, we call them PAR files for each pulsar. And you can also get pulse profiles. So this is an integrated pulse profile for one of the pulsars in the nanograph data set, and there's polarization information. You can grab all of our data at data.nanograph.org. The data for the other PTA collaborations is likewise all public. So I encourage you to go play with these data if you're interested. So we search for gravitational waves by looking at pulsar timing residuals. And so these residuals are the differences between the TOAs that we measure and those predicted by this timing model, right? And so we look at these residuals, and this is a typical plot for one of the pulsars. This is a plot from our upcoming 20-year data set. And so you can see this pulsar, the residuals are like mostly kind of around 0, but there's a lot of low frequency or long time scale noise in this data. And we think that that we can see like visually with our eyes is due to this stochastic gravitational wave background. So in any one pulsar, this background is just going to look like red noise, basically. And it's only when we cross-correlate these residuals with the residuals of all the other pulsars and look for this angular correlation that we can say, like, this is gravitational waves. And just to give you an idea of this, in our 15-year data set, this particular pulsar had a residual root mean square of around 300 nanoseconds when the gravitational wave background signal was in there. And then once we fit for it over all the pulsars and removed it, it was about 65 nanoseconds. So that shows us that most of this variation is due to the stochastic background of gravitational waves. So the IPTA also puts out data releases. So far, the IPTA has released 2 data releases. So they're creatively named DR1 and DR2. So the first one had 49 millisecond pulsars. The second one had 65 millisecond pulsars. These 2 releases, these first 2, have data from 7 telescopes in Europe, Australia, and North America. This plot shows the DR1 pulsars in red, and then the ones added for DR2 in blue. And this is just a snapshot of the residuals of some of the pulsars in the second data release. And the different colors are different frequencies and different telescopes. So you can see right away that many of these pulsars are timed by more than one collaboration because you can see lots of different colors. That's really great. That gives us a higher effective cadence of the observations. It gives us more frequency coverage, more sensitivity. Some of them you can see are also timed maybe just by one collaboration, which is also really useful because we're growing the number of millisecond pulsars in the array. Some of them show a lot of what we call red noise. Some of them look pretty much white. You don't see any sort of like time correlated noise, but we'll take all these residuals, cross correlate them among all the pulsars and look for this special spatial correlation. Okay, so we're currently working on IPTA DR3, the third data release. I am super excited about this data release because it will be the most sensitive data set ever created in the world for gravitational wave searches. It'll have 115 pulsars, and you can see them here. The dots show how many pulsar timing arrays are timing each pulsar, and so some of them are covered by all 6 of the contributing PTAs, some by just 1. There's a much more uniform sky coverage than in the last release, which is really helpful for detecting the stochastic background. And this Venn diagram shows the different pulsar timing array collaborations that will contribute to this data set. So Nanograv in North America, the CPTA in China, the EPTA in Europe, the Indian PTA, the PPTA in Australia, and the Meerkat PTA in South Africa. So this is really pretty amazing. There's a lot of overlap between PTAs, which is really good for sort of like cross-checking, right? And weeding out systematics, but also a lot of pulsars that are only timed by one PTA. In particular, this MPTA, the South African PTA, will add 32 new pulsars to the data set because we did not previously have a lot of sensitivity in the Southern Hemisphere. Okay, so as I mentioned before, the gravitational wave background will look just like red noise in pulsar timing residuals. On the right is a simulation of an injected gravitational wave background, and the colors are 3 different pulsars. This is what this background would look like before we fit for the timing model, this upper plot here. And then once we fit for the timing model, much of this will be absorbed, and we'll end up with this sort of like noisy kind of looking thing in the data. Which is what we saw in that plot for 1909, that pulsar that I showed earlier. Unfortunately, there are lots of other sources of noise in pulsar timing data, and I really don't have time to get into this in any detail at all. But pulsars are not perfect spinners. They show pulse jitter, or like jumping back and forth in phase and amplitude variations for single pulses. There is noise due to the interstellar medium. We could have errors in the planetary ephemerides that we use to barycenter the times of arrival. We could have clock offsets. But the important thing is that even though there are all these sources of noise, the gravitational wave background has special properties that distinguish it from all these other sources. And I am actually going to just skip this slide because I'm looking at time, and I think I don't have enough time to go into that in detail. So let me move on and talk about the results of the recent gravitational wave analyses on the IPTA datasets. I'm going to start focusing just on like the Nanograv dataset because that's the one that I'm most familiar with. But so when we looked at our most recent dataset, and this was a 15-year dataset, this is the result that we got. So this shows the correlated power versus angular separation. And one really important point is that there are 2,211 distinct pairs of pulsars that we do this real analysis on. And this is just a plot that you can like look at visually, but this is not what we actually analyze. We search for this correlated signature in all of the pairs of pulsars. But this is a binned correlation, which shows that we do see this expected positive, then negative, then positive again signature in our data. We were so excited when we saw this because we'd been looking for this thing for, 15 years. When we do the statistics of, how significant this correlation is, we do it in a couple of different ways. We use both Bayesian and frequentist statistics. Basically, they involve taking these residuals and randomizing them. So removing any correlation in the data. So like time shifting them and then doing the analysis over and over and seeing, how often do we get something as significant as this? We find that this is sort of like a 3.5 to 4 sigma result. One super cool thing about this analysis is that we coordinated this analysis with our IPTA collaborators worldwide, and all of the collaborations saw consistent signals in their data at varying levels of significance, and we published all of these papers together on that same day, which was like super, super exciting and a real boon for just the international community and international collaboration. So we did this joint press release in June 2023. It was pretty cool. Like, I think this is a fairly esoteric result, but there were lots of really great articles written for the public about this. They got a lot of press, which was really neat. This is my favorite one. Scientists found ripples in space and time, and you have to buy groceries. Okay, so all of the collaborations found consistent measurements for this stochastic background spectrum. So making this, detection of this signature in the data, like, that's cool, right? It tells us gravitational waves exist, but we kind of knew that. If we want to actually get any astrophysics out of this, right? So actually say anything about supermassive black hole binary populations, we need to measure the spectrum and compare that to astrophysical models. So this shows the spectrum of this stochastic background. These gray violins show the measurements of the spectrum, the power at different gravitational wave frequencies. This dotted black line here shows what you expect for a population of supermassive black hole binaries that are inspiraling solely due to gravitational wave emission. This blue band is the best fit to the data. And you can see it's like more or less consistent. It's a little shallower, but it looks pretty good, right? You can look at this and believe that this is due to supermassive black holes with some more interesting astrophysics in the mix, which you would expect. So this was really exciting when we saw this. This shows the spectral constraints in amplitude and spectral index placed by the Parkes pulsar timing array, nanograv, and then a combined EPTA and Indian PTA analysis. And you can see they're more or less consistent with each other, which is also really exciting, right? This shows that this signal that's in these different data sets is a real astrophysical signal, and we're all getting similar measurements. Very briefly, I don't have time to talk about this much at all, but I will say that even though the spectrum looks very consistent with supermassive black hole binaries, it's also consistent with a ton of other things. So you can also explain this spectrum with cosmic strings, with phase transitions in the early universe, with gravitational waves due to early universe inflation, things like domain walls. So there's a ton of other things you can explain these with, and some of these models can be tweaked so that they are preferred over the supermassive black hole binary model. But the binary model used for this particular plot is very, very simple. So I think the jury is still out. I think there could be some contribution from these more exotic things, but the supermassive black hole binary explanation is kind of like a sure thing, because we know for sure that they exist and we can predict what their amplitude should be. So assuming that this background we see is all due to supermassive black hole binaries, we can make some astrophysical inferences. So if you look at the solid lines here, these show, for instance, this plot, the total mass needed in supermassive black hole binaries. The different colors are different gravitational wave frequencies, but that's not that important. And you can see that high mass binaries with masses of about 1 billion solar masses, or a little higher, are needed to explain this signal. Equal mass ratios are preferred because they produce, brighter gravitational waves. And the population we're measuring is merging at around a redshift of 1 or so. There are huge error bars in this because our detection is not very high significance yet, but we can also place some constraints. One kind of interesting thing is that the strain that we measure is definitely on the high end of predictions that have been made in the past. So this plot shows a whole bunch of different papers that have predicted amplitudes for this supermassive black hole binary background. This is our measured amplitude here, this green band. And so you can see most of the predictions lie below our measurement. So we're definitely pushing like the high end of the predictions. We're not out of the park. It's not like there are no astrophysical models that can explain the amplitude we measure, but we're definitely at the high end. So this sort of implies that, higher mass black holes, more efficient mergers are favored. It could also be that this amplitude will decrease in our next data set, though, as we do a better job of modeling some of the sources of noise in the data. I actually think this might go like a little bit down and be more consistent. And it's also, of course, possible that the background that we're measuring has a supermassive black hole binary primary contribution, but there's a secondary contribution from some kind of cosmological source. And so we're going to answer all these questions in the next data set, at least partly in the next data set, but really teasing this out is probably going to be a decades long process. Okay. So very briefly, I just have like a couple more minutes. I just want to mention that we also do search for single sources in the data. So this left plot here shows the signature that we expect for a single supermassive black hole binary. This is a little silly, but the top is the injected signal and the bottom is the recovered signal. Unless the signal happens to have a period of like a year or something that's covariant with our timing model, this is going to persist exactly in the analyzed pulsar timing residuals. So you can see for 3 different pulsars, if there's a single source, we will get sinusoidal perturbations in the data. The period will be the same for each pulsar, but the amplitude and the phase will shift depending on the orientation of the supermassive black hole binary, the pulsar, and the Earth. Okay, so all of the different PTAs have done these analyses. This is an example of the nanograv analysis. The red stars are our pulsars, and then there are some galaxy clusters and putative supermassive black hole binary sources indicated here. And the color scale shows the distance to which we can rule out a billion solar mass supermassive black hole binary at our most sensitive frequency. And you can see we have like a very anisotropic sensitivity. In some parts of the sky, we can look to about 160 megaparsecs. In some parts of the sky, it's like 40 megaparsecs. And that's just because our pulsars are very non-uniformly distributed. Okay, so let me wrap up very briefly just by one more slide on the continuous waves, and then I'll talk about the future. I just want to point out that one really cool thing we can do with our pulsar timing data is instead of just looking like blindly across the sky for these single sources, if we know of an electromagnetically identified source that is likely to host a supermassive black hole binary, and we have some idea of the orbital period, the distance, the mass, then we're much more sensitive when we search for that signal in our data because we can use those constraints as priors. We've done that for one galaxy called 3C66b. This band here shows the electromagnetically predicted range for the mass right here. And these are nanograv limits with the 11-year data set and the 12.5-year data set. And you can see we're getting like very close to actually getting into the electromagnetically predicted mass region, which is really exciting. So if you are a person who studies AGN or does looks for time variable sources in optical surveys that could possibly be variable AGN, and you find some interesting candidates, you should definitely let a pulsar timing person know, and we can place constraints on them in our data pretty easily. Okay. So the future. So all of the different PTA collaborations worldwide are always working on their next data set. So in nanograv, that will be our 20-year data set. And so we expect roughly an order of magnitude increase in our Bayes factor, or the significance of the Hellingsen-Down signature. On the right shows some preliminary results. The gray points are the 15-year results, and these blue ones are the 20-year results. Again, this is very preliminary, but the error bars are smaller. We expect to be able to measure the amplitude and spectral index much better. This plot here, which I don't have a lot of time to talk about at all, shows 100 realizations of single sources. And this is our sensitivity curve to single sources. And so we have a reasonable chance, to detect a single gravitational wave source. I wouldn't bet a lot of money on it, but there's a chance that a single source could be detectable in this 20-year data set. And even more exciting, At the same time, we're working on IPTA DR3. This shows preliminary results from this IPTA data release, and these are just beautiful. I mean, you can look at this and you can already see how much better you do when you combine data from telescopes around the world than you do with those from just one collaboration. And so this is very preliminary, but this data set will just be beautiful. We'll have a very significant detection, and we will be able to say a lot about the astrophysics of this signal. There's also a pretty good chance of detecting a single source, certainly not guaranteed, but these are sensitivity curves for the IPTA 2025, 2030, 2035. These are simulations of 4 different populations of supermassive black hole binaries, and you can certainly see that some of them lie above our sensitivity curve. This box here, this little square, is 3C66b. So if that has a gravitational wave signature at the level that's predicted by the electromagnetic observations, it would be detectable. This is a big if. These predictions are like very model dependent, right? Like how you fit these electromagnetic data, but this is really exciting. One super cool thing, which I don't have a lot of time to talk about, is that traditionally the IPTA data releases have taken like a very long time to create because we need to combine all the data from all these PTAs, but we have new methods now which don't require that. And so we should be able to produce these data sets much, much faster. I'm just going to skip this because I'm really out of time and just say also bigger telescopes, better receivers, wider bandwidths. The next decade is going to be really exciting. We're going to be timing many, many more pulsars, and the sensitivity will be growing, and we're going to be entering a new regime of multi-messenger science where we can follow up lots of electromagnetic candidates identified with all of these transient surveys in pulsar timing data. And I will just leave this somewhat like provocative time scale of kind of future milestones up. And I'm sorry I didn't leave much time for questions, but I can certainly stay and answer if you.
Yeah, thank you so much, Maura, for this very fascinating talk on pulsar timing array, and looking forward for the 20-year data set, which looks very promising, like the error bars are so small as compared to 15 years. So we might have time for only one question, and other people please write your questions. But if Maura has time and other willing to answer that, we can do that. So Mudita is asking, general question, are there any kind of citizen science projects, initiatives where students can contribute? If not, is it possible to proceed in that direction where it can be beneficial for both ways in terms of outreach and collaboration, for example, the data?
Yes, yes, yes. So I'm glad you asked that. So there is a citizen science project. Well, it's really a student project, not a citizen project, but a project that I have managed for going on 20 years now. It is called the Pulsar Science Collaboratory. And if anyone is interested in doing hands-on pulsar science, this is like a really great place to start. So if you go to pulsars.nanograv.org, I'm just going to share it right here. You can sign up and you can go through like a pulsar course. We have a little 6-week course online. We have a database where we have tons of pulsar search data. And so the initial kind of way you can get involved is helping us look for new pulsars, which is really important for gravitational wave detection. Help us find more pulsars to add to the array. But we also do have some like student research teams that folks have put together doing different kinds of pulsar science, and they're open to anyone worldwide. So if you're interested in this, go to pulsars.nanograv.org. Under Discover, there's a pulsar course. Under Pulsar Search, you can sign up and get online on this database where you can start learning how to search for pulsars.
Yeah, that's great. Thank you so much, Maura. And thank you for your time. It was very early for you, but we really enjoyed your talk, and thank you for being part of this symposium.
Yeah, thank you so much. And if anyone has any questions about involvement in either the PSC that I just talked about or IPTA, just send me an email.
Thank you very much. That was very informative. Thanks for your time. All right, so I think this was the last plenary talk of the session. So now we will move on to a very exciting panel discussion. So the panelists are already here. I hope you can see my screen. All right, so we have a very interesting panel discussion right now, which focuses on the theme of the symposium, so basically women representation in gravitational wave science. So we have with us the panelists who include Dr. Kanchan Soni. She's from Syracuse University in the US. We also have with us Dr. Disha Kapasi from California State University in Fullerton in the US. Dr. Nami Uchikata from University of Tokyo in Japan is also one of the panelists. Dr. Maria Heney from National Institute for Subatomic Physics in the Netherlands. And we also have with us Dr. Lorena Magana Zertusche from Niels Bohr Institute in Denmark. So I extend a warm welcome to all the panelists. In this session in particular, we are going to focus on various different aspects of women representation in gravitational wave science, starting with some of the academic journeys, the career paths, the challenges and achievements that we all have gone through. And let us try to see how we can make the environment more inclusive in gravitational wave astronomy. So I would like to ask first Dr. Kanchan Soni to say a few words. So I have some, okay, I forgot to mention the code of conduct. So this is something we should abide to during this session and all throughout the event. So this symposium aims to foster a respectful and inclusive atmosphere. So we are all expected to behave respectfully and free from discrimination, harassment, or retaliation, any kind of inappropriate behavior or bias towards gender, sexual orientation, disability, physical appearance, body size, race, nationality, religion, etc. will not be tolerated. So we also support the LVK, the LIGO-Virgo-Kagra Collaboration Code of Conduct, the policies of the LIGO Scientific Collaboration Diversity Committee, as well as the Diversity, Equity, Inclusion Charter of the Gravitational Wave International Committee. So let's move on to the session right now. So I would like to ask Dr. Kanchan Soni, who is here with us. Kanchan.
Hello.
Hi. Yeah, we can hear you. So yeah, I wanted to ask you about what do you think women representation in gravitation science means today?
Ah, that's very interesting question. And first of all, thanks for having me over here as a panelist. And it's great to see a lot of people joining and then participating in this wonderful symposium. To answer your question, I think according to me, at this present time, women's participation has gone a little bit more. I mean, we are seeing more number of people joining in as not just as a research scientist, but also making up to at a higher positions like as faculties, as leaders. And what I think the current matter we discuss is women's representation is not anymore about awareness, but it's about the accountability. This is because I feel if you can move to the next slide. Yeah, this is why I'm saying it's because we have seen a massive number of people joining, starting from bachelor's and then master's, going up to PhD and also going for postdocs. So certainly the number has gone up. It's mostly because of the science popularization and women participation in multiple ways. So we are seeing the visibility of women participation more. Whether it's a small collaboration or a larger collaboration, there are people who are more invited to be speakers as PIs to many projects, and also they are taking up collaboration leaderships. Apart from this, I see that the mentorship that used to be discussed in a very close environment, that's now open, and because of this, many people are feeling comfortable to join and take initiatives in public outreach or in taking up some of the interesting tasks, and then leading up those projects. Uh, so I think beyond just the numbers, it's about like asking the questions, like who is taking up the scientific agenda and major project roles, and then who's making decision. Everything has changed over the past couple of decades, and this is a good sign because it shows that we are moving in forward.
I totally agree with you. Yeah. So definitely we have come forward from what we also heard from the previous talks, where we had really a handful of female contributors to science. Currently, the numbers have gone up. We also need to keep in mind that, I mean, not all representation comes from the same kind of career stages, right? So there are, of course, existing problems. But as you mentioned, so there is definitely much more visibility right now, more mentorship opportunities, and also we need to ask questions now which are more about what are the leadership opportunities for women going forward. So I mean, also the panelists, please, to the other panelists, please feel free to unmute yourself and comment if you would like to. So I think we also need to mention about what we call the leaky pipeline model. So basically, as we go forward in career, we see a lot of women who are or young girls who are signing up for STEM disciplines, taking interest and also doing well in their basic education. But as we go forward, so there are many other problems, and so this leads to a leakage in the number of fraction of women who are contributing to more senior positions and leadership positions. So I think here in this slide, so there are some topics that we want to take up. Do you want to say something about these?
Yes, I mean, I completely agree with you. There's definitely a problem with this whole system, and there is definitely one thing we see and we notice at every stages is, and this is what the representation of women, it just drops with the seniority. Like more number of people join as a student, as a postdoc, but then over the time, the number just narrows down. So even though relatively speaking, like over the course of 10, 20 years, the number has gone up in each stages of the academic career, but still there is still a number that doesn't make it up to quite high. And I think the main reasons, what I think is because there are many challenges that women face at different stages. When it comes to early career scientists, there is always a problem of taking up leadership and then showing the visibility in different ways. So, for example, if you're talking about larger collaboration, most of the time, what happens is you may be investing a lot of time in doing projects, but it may happen that you may not get the right kind of recognition, and because of that the credit diffuses for the contributions that is made by early career scientists, and not many people get to uh, move to the next step, which is like taking up some responsibilities and then maybe leading up most of the projects. So it usually works out for us little bit senior scientists, but what happens is for early career scientists, the credit diffusion actually hurts them quite a bit, and because of this, there is like a visibility gap. Um, a lot of people lose motivation in pursuing science or whatever they are interested in, and this basically helps in the next stage, which is like in a postdoc phase. There are many challenges over there, but if you have already lost some of the bits in the previous stages, then in the next stage, the difficulty level just goes a little bit up, like because postdoc phase is meant for a very short duration, so you have to be quite quick with things, and then there are like many expectations that is um, asked from you. And there are other challenges as well, like mobility, how flexible you are to move to a different country, whether it's there are some other barriers or not. Those things one has to face. Also, there is like a visa instability and then job uncertainty, which makes people, women scientists, in a stage that they want to choose the right career path, and sometimes they drop out because of this reason. The other problem is two body problem. Like this is a stage where people make a huge transition in their personal life, and if their partners don't reside at the same place where they are working, or if they are interested in working in some place and there's some communication gap, then these things also affect a lot of our decisions in taking up the next steps. So yeah, I feel that because of all these issues, a lot of talented people, they end up either quitting or switching to some other jobs, not just because they are not talented, but then it's how the circumstances are, and this creates a huge problem for, I guess, every stages of the life. Yeah.
I would like to pause here. I think Disha also has her hand up. So I would like to pause here because you raised many, many important topics right here. So currently that are crucial for understanding the women representation in gravitational wave science. I totally agree with you. So in particular, giving recognition to early career researchers is important in their consequential development, career development. And we also need to think, I think many of these questions have been raised. So certain measures are also being taken. I know from the LIGO Virgo Kagra collaboration side that this kind of the asking for recognition, this has been raised to the spokespersons. And also currently there are some LSC Academic Advisory Committee, which does ask, that provides, some kind of certification for recognition. Because if you are a student and you're working for a collaboration of over 18 countries, then it's often that, your recognition may be lost in a paper with hundreds of authors. So this is definitely a cause of concern. And what you mentioned about postdoctoral positions, so this is also a very important point because there are, problems of intellectual and geographic mobility. Then you have to rapidly adapt to different languages, cultures. Um, and there is, of course, unending bureaucracy that you have to go through. So I think definitely, so these are very important points. I would also like to ask others in the panel to comment if you like. So Disha, definitely, please go ahead. I think you can unmute yourself.
Yeah. Can you hear me?
Yes.
Yeah, I just wanted to add to one of these reasons why many women scientists might drop off is also like when I was applying for postdoc positions, one of the key things I was looking for was which countries or states, if I'm looking within US, are liberal, because there are a lot of states that have like specific laws against abortion, LGBTQIA+. So it sort of becomes like when you start putting those constraints, because you do not want your personal life to be affected by the place you're residing in. So when you start mapping these things out, it sort of becomes like a bottleneck where you have like probably 10 places you'll apply to or can apply to, but also there might be funding issues or they're not hiring at the right time and you're not at the right place. So a lot of these might become a backlash for women scientists to like drop off after their PhD careers and maybe transition to industry as well. So I just wanted to add that, because it's not only in the US, it's across like many other countries also. When I was applying, I had to look through like different places to see what kind of like other government laws are there that might just affect my personal life or so with my partner.
Definitely. Any other panelist? I think,
Yeah.
okay, yeah. Lorena,
Can
please go
I?
ahead. Yeah.
Yes. Another thing that I think it's important also to take into account is that because this the representation drops as the position level becomes higher, then that also it creates kind of a cycle where, you know, if you don't see yourself represented in leadership, then it's going to be, you know, you're less motivated, let's say maybe, or you're less encouraged to continue forward. And I've noticed this a lot for even at postdoc level already. I have had at least, you know, one master's student say, "Oh, I've never met a female postdoc in gravitational physics," which was very sad, but also, you know, it's very likely that a lot of people have had the same experience. So I think it's also important the group that you are in. To always like try to make it inclusive also in the number of women that are represented, because if there are no women in your group, then it's difficult to attract other women, because why would you want to apply there, right? The fact that there are no women makes it feel like maybe there's some reason why there are no women instead of just some fluctuation, for example. Yeah.
Yes, I totally agree. So I think this is why we need women role models and ambassadors. Even in my institute, I think this is like a funny history. In 37 years, we have not had a woman professor until I joined. And literally, when I joined, people told me women don't go there. So after I joined, now more and more women are applying for faculty positions. So I think definitely we need to break this kind of, glass ceiling that exists, and particularly with women role models, we can deal with that. Maria, would you like to go ahead?
Yes, I think jumping off on this point, I think the problem is then a little bit getting over the threshold, right? Because I think you kind of need a critical mass of women to break this, I guess, unconscious bias that people have in hiring committees, where especially if you're hiring for a faculty position, it is very difficult to compare people head to head, because everyone is bringing something different, and people have different research profiles. People have different experiences of leadership. So I think also from my perspective, and I think that is maybe specifically a Dutch perspective, where there was a policy effort for the last 10 years to meet certain gender targets in the hiring of faculty, you kind of need to support this process with some formal or informal policy that is saying this is where we want to go. And then there is a certain groundswell of, I guess, will to reach this critical mass that you need to also, I think, get more people into the door for postdoc and for a PhD position, just by having female role models available in the field.
I totally agree with you. Thanks for raising this point. I think, yeah, this is very important. In particular, also when I joined my institute, a lot of the things were not really, designed to have women in place. And once you start raising these questions, you see that the environment becomes more and more inclusive. So I think, like, definitely what you said about the critical mass, this is really important. Isabel is raising her hand. Yes.
Yeah, I just have one question I want to make to everyone connecting. This question was done to me by a female colleague, a little more senior than me. She asked me, not taking into account, let's say, collaboration articles, how many research articles do you have with a female co-author? I was thinking for a while, and my answer was 0. Can you imagine the impact? So I just want to make you this question, and I want you to make this question to your colleagues.
Yeah.
Because that's really important. I mean, if we don't count female talent, even in scientific papers, that's shocking, no? If we normalize that not having women in our projects is okay, it's very, very dangerous. So sometimes more than, let's say, trying to educate adult people, that can be hard and that can be annoying. Okay, not everyone is super happy to receive critics or not always we are able to express them in a proper way. But I like the point of making questions. Very simple, obvious questions. And this one was part of a shocking moment for me. Even if, as you say, for example, also here in Valencia, the Department of Astronomy and Astrophysics, where I did my PhD thesis, only had the first permanent female researcher a few years ago, and was the woman chairing the office with me during my PhD. So it's, I mean, we are advancing. Some things have been done, and I think regulation is very important. Not let nice people behave good, but just also include in regulations things that we think are important. But this question was for me like a shocking moment. So I just want to share it with you.
Thanks for raising this point. So I think this is also very important to keep in mind that we ourselves do not suffer from any unconscious bias. So it's important to raise awareness that whenever we are, organizing meetings or, hiring students, we also need to keep in mind that we are not neglecting some of the students who may be, women or who may need some mentoring to bridge the gap. So this kind of, discussions help us to, develop this kind of an awareness. So I think this is very important. I myself, in my research group, I have 7 PhD students and they are all boys. This is surprising because I myself, being a role model, I thought that many women would actually step up. But again, I want to raise the issue that gravitational wave astronomy itself is extremely vast and diverse. There are many different aspects, like there's data analysis and there's theoretical modeling and there's computation and instrumentation. And if we look at these particular ratios of like gender ratio, it is not uniform. So I think we know, I myself being from theoretical physics, I know that we have a very, strong problem of, we have women less than 15 to 20% globally. So I think this is a global problem. Probably in mathematics is the same. I think it's slightly better in observations and data analysis. Instrumentation, I think there are people here who may be able to comment. I don't know much about instrumentation, but yeah, I think we also need to think about these different, multidisciplinary aspects of gravitational wave science. So tomorrow in the focus session, we'll probably discuss this a little bit more. Are there any other comments from the panelists, or maybe, yeah, Maria?
Yeah, I think to jump off on this, because I think I'm a data analyst myself and a theorist, but I am spending my day mostly with experimental gravitational wave scientists, because this is just where the majority, I think, of the Dutch contribution to LIGO and the Ancient Telescope is focused. So I can tell you that at least for us in the small microcosmos, we actually have on the faculty level a parity between male and female faculty members for the data analysis, but in the instrumentation efforts, that is much worse. We have many more male faculty than female. And I think that is also maybe specific to the country, because I think especially in Europe, for physics, that is, I guess, somewhere on the border between experimental physics and engineering. I think the pipeline somehow seems to be even leakier.
Thanks for making that point. This is interesting to note. I mean, sometimes I feel like maybe this has to do with the fact that, theoretical physics or data analysis gives women more freedom of mobility. You can work from anywhere. Instrumentation might be difficult. You have to spend long hours in the lab. But I still cannot explain why theoretical physics has so few women. But I think this is like interesting to get, the discussion going. So I think we can move on to some of the other aspects that we are discussing here. So we want to talk about the demographics that we have collected in the past few years. So this is from the LIGO scientific collaboration. Dr. Disha Kapasi, do you want to comment on like what we have learned from these demographics or more?
I think I just have one point to say about this. So this is what you see right here is the gender representation from statistics that was collected in March 2025. And I do not have a reference over here, but if you look at the statistics that was published in 2015, which was exactly 10 years ago, right around the discovery time, um, the left side pie diagram that you have, the scientific collaboration and the LSE leadership, the women contribution was just 5%. So we have grown a lot in the last 10 years is what I was trying to point out by putting this graph in, that in the decade since the discoveries happened, a lot of women scientists and researchers have joined the collaboration, but also have moved on to senior leadership positions and council positions, which is reflected in the pie chart for the LSE leadership. There's still a long way for us to go, because you can see that if you look at the gender identity by the career stage, we still do not have like equal representation across all of them, but at least there's been a positive rise since the discovery, and we're a growing collaboration also.
This is very interesting. Thanks for sharing this. Also here we see by career stage, like pretty much we still see this leaky pipeline model. This is very useful demographics to see how it changes from going from student to graduate student, postdoc, faculty, research. I see that, in fact, for technicians, it is also quite
Yeah, I think the
bad.
starkest, the main thing would be the postdoc to faculty, where we've been talking about the leaky pipeline. You can see how at the postdoc level, there's more or less getting close to a 50-50 representation, but the minute you push it to a faculty position, it's really low.
Right, right. So this is where the crux is of the problem. Also, we see here outreach is pretty well balanced. So I think these are some things to keep in mind. Isabel, do you want to make a comment here?
No, I just wanted to say that, well, I work in outreach and I am very happy to see that we are doing not so bad. So I think it's partially is because outreach, I mean, I would say the good and the bad, partially because in outreach the environment is less competitive, so that attracts more diverse people, I think. On the contrary, it does not matter too much for some people, so that's also why some people go thinks it's less competitive. So but we need to balance that. I think if you participate in some outreach events and you really talk to people and you feel the enthusiasm, then you start thinking this is not important as any other step in the whole chain. But I really like the fact, and I say very widely, all the people in outreach I have met in my collaboration and in other collaborations were generating a very kind and inclusive environment. And that's something positive.
This I totally agree. So I also work a lot with the LSC. Not only like LIGO Kagra outreach teams, and I think they're extremely supportive. This is the kind of support we also want in academia, but unfortunately, this is not the case. And as you mentioned, I think competition has a lot to do with it, because as you climb higher in career, there is this fight and struggle for recognition. So I think this definitely plays a role. Before we move forward, is anybody else want to make a comment on this demographic? Okay, if not, then we can look at the other upcoming third generation detector, Cosmic Explorer, what its demographic is telling us. So this is also very interesting. Does Disha want to say something about this?
Yes, I can say a tiny bit. So Cosmic Explorer is a third generation detector, and the Cosmic Explorer Consortium consists of members that participate in Cosmic Explorer activities. So the response that you see here is just 31% response rate. So there are at the time of when the survey was sent out, there were 542 members and only 31% have contributed to this survey. So this is what you're seeing. It could be highly skewed because not even 50% have like contributed to this survey. But from what we have over here, I think it's very similar that at the PhD and postdoc level, there's still, a fair few women scientists that are there. But as we go to like, faculty and scientist staff. So when I talk about scientist staff, I'm talking about scientist staff at the either contributing to some works at the site or are just doing only technical work for Cosmic Explorer, designing vacuum pipes and things. So there's a starking difference between the gender representation over here. But yeah, I would say take this results as a pinch of salt because the response rate is just 31%.
This is interesting. I just wanted to ask, like, is there a possibility to make such surveys compulsory, or probably it's not?
I don't think any organization makes it compulsory.
Compulsory, right?
Like I've been part of LSC, Cosmic Explorer, and OSGRAV, which you'll see in the coming slides, and none of the surveys are ever compulsory. They strongly recommend that you do it, and it usually takes about 10 to 15 minutes, which is why I think many people drop off as well, because it's not a quick 5-minute survey. It usually is loaded with a lot of questions, and some of them make you think because you wouldn't have thought about a lot of these aspects of are you in a welcoming environment, or do you feel that you're equally represented? So it's a loaded question that actually takes some time, even though it's only 10 minutes. So I think many people just like leave it. But I think in the next year, by 2027, you'll have a more you'll have a newer statistic that will come out from Cosmic Explorer. So that would be interesting to see what those say.
Thanks a lot. Yeah. Does anyone else have any comments on these demographics? Okay, if not, then let's move to the Kagra collaboration in Japan. So Nami is here with us. So maybe Nami, you can tell us more about how this scenario is in Japan.
Yes, so yeah, I'm a Kagura member. The detector is located in Japan, but it's an international collaboration. So we have started the demographic surveys since 2018, and as we can see, always female ratio is about 10%. And until 2022, there was no female faculties in the Japanese affiliations. And we didn't have a survey last year, so the latest one is 2024. And actually, the participant rate is not very high, but yeah, it's still, the female ratio is 10%. And also, yeah, I think only there are just a few female faculties in the Kagura collaborations, and yeah, we only have 1 or 2 female members in the management level. And also, I belong to Institute of Cosmic Ray Research, ICRR. Yeah. And this is the main host institute of Kagura, but yeah, totally there are 30 members, including students. But yeah, actually, I am only the female researcher in this group. Yeah, but fortunately, there will be a few new female postdocs. They will be joining this year, so I hope this female ratio change gradually. Yeah, that's all.
Thank you. This was very interesting. What do you think leads to such low number of female faculty in the institutions? Is it lack of interest in this kind of, career path, or is there, or maybe you can tell us if Kagra is making any active efforts to, have a better gender ratio?
Yeah, actually, I don't know the reason why we have so a small number of female. The one thing is maybe cover is just a bit young collaboration compared to LIGO. So
True.
I hope this will change in the future. So and
maybe there is also lack of awareness about the project because it's a new project and there needs to be more outreach so people know
maybe
about it.
Yes.
Disha wants to make a comment.
I just have a question maybe to everyone because I thought of it now. So especially resonating with what Maria said earlier, that this change has to come from the hiring side when you're hiring female researchers in institutes. So if there is a job ad put out that they're looking for women researchers, depending on whatever level it might be, like postdoc faculty or a scientist staff, how would you navigate a situation where the institute is genuinely hiring because they want to move towards a better gender balance, or they are doing it to tick off a DEI box? Because sometimes you end up getting into that position, but you might be in such a hostile environment because it's basically meant to be a tick mark. So I think my question is to other senior female researchers on this panel and this call that, how can we better either put a job ad, or how do we navigate such situations? Because it has happened to someone I know personally that they joined a position but later found out it was sort of like a DI take. So it was a very hostile environment for them. And then they quit and moved to industry.
Well, I can say from my personal experience because when I joined here, I was the only woman faculty for quite some time. I did not face any particular, so this was also like I did not know what to expect when I joined here because being the only among the youngest and also the only woman faculty, it is not particularly inviting when you have only male faculty in a faculty meeting. You feel intimidated, right? But I think it is important that we do not take this we do not expect the most welcoming environment when we walk into an institution. So I think definitely I know that now that there is more awareness. A lot of institutes which have zero faculty, they are actually changing their advertisements and making it giving more information about facilities like having a creche and childcare facilities, or giving a formal statement that we welcome women researchers, or we have an inclusive environment. I think this definitely needs more awareness, that a lot of institutes don't even know that it is a problem that you don't have women scientists there. So Isabel, you want to make a point?
Yeah, so there is not a unique answer. I think that's the first thing. It depends a lot on the person, on the environment. For me, there are 2 points here. One is if you feel alone, look further not to feel alone. If you need to go to the whole world, it doesn't matter. Go to the whole world. But you are not alone. Don't feel alone. That's super important. Because recently I write a book with some female researchers in STEM in Latin America, so Mexico, Brazil, and it's another continent, but we share the same problem. So you are not alone, even if you look to go further, even to the whole world, no? And then the second thing, this depends a lot on the problem and the situation. But for example, in my case, I don't see that family or conciliation, let's say, of personal life is included in the environment in my university. So I am bringing my daughter to everywhere. So they are people, if they were not aware that children exist, they will know that my daughter exists, at least. So obviously this is not possible. It's a little like joking, no? Like make things visible in the way you can, in the way you want. Obviously this is more like a suggestion, but for me it's important. It's like, I don't know, if you think it is important, to show something pink, like the color, just take something pink and put that in the middle of the classroom. But how to do that is not always easy, it's not always possible, it's not always like you want to be in the focus. So, but I just normalize things and try to look for allies, even if I have to go further.
Thanks, Isabel, for making this very important point. I think it's very important to highlight that no matter where we are in this global collaboration, we are not alone. I also see that currently, like, I'm one of the leads for the DEI representative for the Gravitational Wave International Committee. And here we are basically exchanging notes between the different collaborations, sharing the best practices. And there is so much to learn. I think we know, now what works and what doesn't work and what we need to improve. So it's very important to reach out to the global collaboration. Kanchan, you want to make a point here?
Yeah, I just have a quick comment on what Disha raised a question. I think it's a serious problem, like not familiarizing with the system and then applying to those places and later on getting to know that, okay, it's not a safe place to work. That's a serious issue. And I think it's this issue pops up in all the stages, even if you're applying for a postdoc or a faculty position. But I think what could help in such cases is if we personally visit these places and then get familiarized with the people and at least have some contacts and get to know through the lens of either student or faculty or just in the general, like people who are working in the institute, that can help in certain situation to make our decision more concrete, because this will avoid the further like future problems. That's what I believe. But yeah, sometimes it may not be easy to make this kind of move. But yeah.
Thanks. Yeah, Maria has her hand up.
Yeah, so I don't think I have sort of like personal experience with this, because when I joined NICEF as a permanent staff, there were already in the general faculty quite a lot of also young women hired in the previous years. So there was a cohort of peers that you could talk to and that you could talk about these things with, and it felt very like a very safe environment, even though personally in sort of like the small gravitational wave bubble that I see every day, I'm the only female faculty. I think what I would probably advise, if you are hired somewhere as a first female faculty and you don't really know if they genuinely want you for this position and they genuinely want to increase the diversity of the faculty, or they just want to tick some kind of DEI box, would be to ask them in the hiring process, in the offering process, point blank, where do you see me in 5 years? Sort of like, what are my what do you see as my career advancements over the next 2 years? How do you see my role in the organization? What kind of responsibilities are you going to give me? And I think that will give you some kind of indication of how they are going to treat you in the future when you join.
That's a great tip. Thanks, Maria. So I think we will move on with our demographics. So we also have demographics from OSGRAV, from the OSGRAV collaboration. So who would like to comment on this? Disha,
I can do this.
Yeah, sure.
I think the key thing I wanted to show over here is the bottom right graph, which shows the percentage of female researchers since the birth of OSGRAV, which was in 2017, if I'm right. And you can see that it started off somewhere around 25%, but in the last just 8 years, it has grown to almost 40% representation. And I think this was really nice to see how things are moving along, both when I try to show like the LSE, which is the bigger collaboration, and OSGRAV, which is I think around 300 people or so, including admin, support staff, and all the researchers. So this was really nice to see. And I think the bottom left graph still shows some similar things about like those bottleneck issues that we've been talking about, that we see a lot of students in the, we see a lot of women researchers in the student and PhD phase, but as we move on to like other more long-term career options, then we start to see a drop off in representation. And then the main thing I wanted to show was, I think if you look at the top bar graph, like the horizontal bar graphs that are there, you can also see like the breakdown in leadership positions that is there. So for example, the second one, which says leadership position for percentage women, the ratio for women, men to any gender is 32, 68, and 0. And they're trying to achieve 40, 40, 20. So we're not that far off being the 40% representative. And the same for like the gender breakdown overall on top. So I think this was really nice to see like how across many collaborations there has been like a positive uptick for gender representation.
This is great. I think we have a lot to learn from OSGRAV, and I think OSGRAV should definitely share their best practices with the rest of the collaborations so we can.
Oh, I think
start
the
to take
highest is sorry to cut, the highest is the third one, which says % new recruits women plus, and their target was 33 for the annual year, and they achieved 48 new hires in women, which is more than one or around 145% that they got. So I think that was really nice to see that, you know, there are all these other collaborations making very strong efforts to reach a very balanced gender representation.
This is great. Thanks for sharing this.
Debbie, may I add something
Yeah.
short? I think here is important, and at least this is something I am starting to do, not only the numbers, but the performance among each group. So, for example, in mathematics, as you mentioned, the number of women has been reduced year by year since my time, because when I started we were even more, but well, this is due to data analysis boom and so on. And we are having less women in the classroom each year. I cannot change that once I start the academic year, no? But what I can do at the end of the academic year is to check the performance, the average performance of women and men. And also to be like self-conscious if I am doing some bias. And I am very happy to, and I say this because I am very happy to say that the difference in the subject I gave the last year of mathematics degree has difference just in the second decimal. So 7.9 whatever, 7.9 whatever for both men and women. So that means that at least in that regard, I am valuing equity, equally both groups. So it's not only about the numbers, but also about the performance or the value that we do in each group. And I think, I don't know yet how to include that in the statistics, but I think we need to go a little beyond just these critical and not nice numbers, no?
Thank you, Isabel, for sharing that. So I think we can move to LISA collaboration. So Lorena, do you want to tell us more about the demographics in LISA?
Yes, so the first demographic survey that they conducted was in 2023 before LISA became a more formal consortium. And the only data we have from that that I saw broken down by gender is the top right chart, where you see that 23.6% identify as women for gender, and then 72.2 for men. And then you have smaller percentages broken down by non-binary, other. So it's not great. It's a bit lower than I expected because I've seen a lot of representation of women. But also this is only a 32% response rate. So like with I think it was the LSE that also had, only 1/3 of the people actually replied to the survey. So there is definitely some bias on that. So they have not conducted another like demographic survey per se, but there was the consortium was formalized more recently, and with that one had to sign up to be either a core member or community member. So with this also came some demographics that I think they were optional, but I'm not 100% sure on this. because I know different countries have different laws regarding what information you can actually ask and what you cannot. So that's the bottom left plot. So that's actually the more recent one. And so here we have it broken down by gender. So you can see again this bottleneck where if you look all the way to the right-hand side, you have the PhD student, which here in a way, it's the one that's the youngest, the earliest career. So you see for women, it's 6.3%. When you move to postdoc, it drops about a percentage or so. And then when you get to tenured member, that drops up 4. And tenure track is less than 1%. So you also see that decrease. And in the other, I just want to mention, so the second to last category, other, it includes also master students. But you can still see overall it's quite a small percentage. So yeah, I think there's definitely a lot better than we could do. But hopefully, you know, with the new consortium starting up and with more efforts, hopefully this number will change in the next couple of years.
Thank you very much for sharing these statistics. So I think this is very important to have in mind, like to have a guideline on how to move forward from here. So yeah, thank you very much. Does anyone else have any comment on this one? If not, I think we can move on to the European gravitational wave community. Of course, we heard also from Isabel in her talk about Virgo collaboration, but we also have with us Maria. So Maria, maybe you want to tell us about the demographics in the European community.
Yes, so I've tried to find some information, official information about the gender demographics of Virgo. And I should preface this by saying that I'm a fairly recent Virgo member, has been a LSE member for a long time. So try to crowdsource a little bit if people know of information who are involved in the DEI efforts, know of information that might be available elsewhere. Personally, I could not find anything. I found information that told me that there have been discussions in the past of collecting this data to kind of get an understanding of where Virgo is and how the situation evolves in terms of female representation in different age groups, in different aspects of Virgo science, in different leadership positions. And there were discussions to either, similarly to what Lorena described, happened during the sign up for the new LISA consortium, to try to collect this information from the Virgo members themselves through the Virgo member database. And there were separate discussions of, similarly to what was previously presented for the LSC, to also send around surveys that could help assess the state and the evolution of diversity in Virgo, not just with respect to gender, but also with other axes of, let's say, underrepresented community. From what I've seen so far, neither has been implemented. And I think one of the reasons is also that it's not 100% clear how to make this compatible with the data, or the very strong data protection laws in Europe. I have been told that after the transition to the IGWIN, a new iteration of this demographic survey is planned that then basically will involve IGWIN members from the US, from Europe, and from all over the world. So currently for Virgo, we do not seem to have the kind of data that kind of tells us how women are represented in different parts of the community. And for the Einstein telescope, their sort of like DEI efforts themselves are still in quite a nascent state. So I've also not seen any information about this data being available. And then on the next slide, to maybe give a snapshot for a particular part of the Virgo community, which is the Dutch National Gravitational Wave Program, which is hosted at NICEF. So NICEF is the Dutch National Institute for Subatomic Physics. So hosting not just the GW program of the Netherlands that is defining contributions to Virgo and the Einstein telescope and delivering them, but also doing the same for contributions to LHC and other particle physics experiments, astroparticle physics experiments, etc. So these are numbers that basically come from the employees themselves, from the intake form that we all had to fill out when we were hired, and we had to tell the organization information, something about our gender identity. So on the left-hand plot, this is the gender ratio in the Dutch National Gravitational Wave Program in relative numbers. And here you clearly see the leaky pipeline, because the total numbers, the situation isn't great, but the situation is better than it is for the permanent staff. And as I previously mentioned, here you also see kind of an effect what the research focus is, which is strongly focused on experimental gravitational wave physics, where at least in Europe that seems to be currently even more leakier in the pipeline than in data analysis and in theory. But there has been some concerted effort on the national level in the Netherlands to invest in more gender diverse science over the last 10 years. There have been explicit gender targets for faculty recruitment in the sector plans for scientific research and university education that the Dutch government has. And for the gender ratio by age group for all the NICGE faculty, so this includes gravitational wave, particle physics, particle physics, everything, you clearly see that the lower you go in age of the permanent staff, the more balance between genders you get. And for the youngest age group, so the under 40s, we actually have now achieved gender parity. So presuming that this picture holds and there's not going to be at some point maybe some reactionary movement against diversity, equity, and inclusion, we can reasonably expect that within the next 10, 20 years, we are going to be maybe closer to the 50-50 than we have in the past.
Thank you very much. This was very informative and very interesting. Does anybody else want to comment? Because we are almost at the end of the hour. On this slide about Einstein Telescope collaboration, Virgo or Dutch National Program. If there are no comments, then I will, just a second, I don't know what I did. Did I stop share?
No, you're sharing. Yeah.
It says my screen sharing is paused. Okay, I will just share again. All right. So I think we're almost at the hour. So I want to ask the panel who's here to, we want to introspect and think about what we can do to move forward from here. So I think we have now a good idea about, how we are placed in the different collaborations. The demographic surveys give us a good idea about gender ratios. We have also discussed some of the problems and challenges that we face as we go on with our career. So do we want to make some comments about how we can improve this or what we can do to move forward? So I think we already discussed a few, first of all, I think even in OSGRAB, we saw that outreach plays an important role, first of all, to raise awareness. There are also active programs which also guidelines for recruitment in many institutes, which tell the panels to keep in mind to remove any kind of conscious or unconscious bias when hiring. Yeah, I will let Lorena go ahead and say, yeah.
Yes, thank you. Yeah, so I think one important thing that I've heard mentioned before, and I think the older I get, the more I realize how important this is we cannot do this alone. I feel like a lot of the effort that we've done has been alone in a way, in a generalized way of speaking. But I think also having male colleagues who are supportive towards this, because not all of them obviously are going to make us feel uncomfortable or are going to be on the other side. But I think finding male colleagues that can support us and our allies essentially is important. So one of the things, for example, that was mentioned earlier about what if you're the only woman in an environment where it's male only and you do not feel welcome. Well, I think one way is to try to find male allies in that institution, and of course female allies at other institutions through mentoring programs, for example. But another thing that I think that I'm not sure how to solve, and maybe also people can comment on this, is to do these outreach efforts. I've also noticed that for outreach, it's always very heavy. Well, I guess I should say not heavy on female, but it's quite equal representation. But if you look at the numbers, percentage-wise, is more women than men doing outreach efforts. And so as much as I think all of us enjoy doing that, that also can put a strain on the amount of time you have to do science and other things, while our male counterparts maybe have more time to do science because they don't do outreach, or they don't care about, showcasing minorities in physics. So I think it also to have these male allies to kind of help you also with outreach and try to come together in a way that also gives you back some freedom and some time, but also puts you as a role model. Yeah, I think that's one direction we can take towards trying to solve this issue.
I totally agree with you. And I also think that you raised a very important point that it's not about, I think it's not about, the problem is not about male or female. It's like the gender bias and patriarchy is a system, and it is equally, I mean, often very much, there are men standing up for women, and also there have been cases where there are women who are supporting patriarchy and gender bias. So I think we need to be very careful in defining where the problem lies. Isabel, do you want to make a comment?
Yeah, just a short comment. I don't see a problem by itself on women putting more time in outreach. I think the problem is that if a man does outreach, he's doing great. But if a woman does outreach, it's not doing so great. So
I agree. Yes.
it's. I think the point is more like how you value contributions, and in this sense, because for example, I do a lot of outreach here in Spain, but the famous ones are eccentric boys doing crazy things. I don't want to do crazy things to attract attention. My science is enough, but the way media promotes, let's say, videos and activities and so on, is getting us women less significant sometimes. So I don't think the problem is really like what do you with your time? Is your work value? And we check. So, for example, if you organize something like outreach national TV, that's having a lot of impact. I think that's really important, no? And then it's very hard to see women there. I also know that it can be because women, we don't want to be in the focus because we receive more attacks. It's not like we don't want to be in the focus per se. It's just that we are tired of attacks and haters and blah, 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 blah. But I am insisting a lot now here in Spain and with colleagues on how we value and recognize management tasks, for example.
I totally agree with you. In fact, when I started doing more and more outreach, I was warned by other female colleagues saying that, at least in India, this is true, that if you do more outreach, then you will not be taken seriously in science, because you will be like tagged for, as a science communicator. And you could be as well, scientist as well as a communicator, but often you are taken less seriously. So these are issues we really want to, keep in mind. Disha, please go ahead.
I just have a quick comment to say that for anyone who's on this call, always reach out to any of the other female researchers, be it in gravitational waves or outside. They're always ready to help and have a chat with you and, give you tips and guidelines. I've often found friends outside of gravitational waves also that have, given me tips on like career advice or on CV proofreading. So every female researcher, despite the country or where they are, they're always very welcoming and they want to help you grow because they want to see these numbers, show up in the gender balance. So don't be afraid to reach out to anyone.
That's a very important message. I think we also have more and more mentoring programs coming up in many collaborations to handhold, the young early career researchers, particularly women, who want to, go ahead in their career. So thank you for these messages. Are there any comments? Anuradha, do you want to say something, or are there any questions in the chat? Because I'm not able to see.
Yeah, no, thank you so much for everyone in the panel, and it was very illuminating and seeing all the demographic data. And I also appreciate the thoughts you shared with us, like how we can improve the gender uh, numbers. And yeah, so it was very enlightening. And I hope the audience also learned something about what we are doing in gravitational wave and where we stand in terms of numbers, and hope that with in future we will do better with more effort, as we learn from maybe Osgrave is doing wonderful, so maybe we have something to learn from them. Yeah, so I don't see any questions in the chat, but we are also kind of on top of the hour, means we are passing the hour, so maybe it's a
Right.
good time to wrap up the day.
Just before we wrap up, I have an idea. So can we, like all the panelists are here, and if anybody else wants to be on a Zoom feed, we can take a picture. So please put on your cameras so that we can take a picture. Woman power.
Yeah, please,
I'm so
everyone,
glad.
open your, if you can, if you are in a good
Yeah, if
chat,
you
yeah,
want to be
please
in
do
the
that. And
group
we'll,
photo, please put on your picture so we can have a memory to keep with us. And also, it's very overwhelming to see the participation, because it has been really across collaborations all from all parts of the globe. So thanks to all the participants of the previous session, of the panelists, and also the participants who sent questions. Thank you all. So I think I will go to the gallery. All right. So let me take off my headphones. All right. So smile. I'm going to take a photo. Just give me a second to save it. One more. Thank you. Thanks. Yeah. So I think I thank all the people from this session. So just to remind you that tomorrow we will continue with the focus session. So maybe I will briefly share my screen just to show that tomorrow we have, can you see? I hope you can see my screen. So tomorrow we have the focus session where we talk to women researchers from various different aspects of gravitational wave astronomy, from instrumentation and theoretical analysis, data analysis, observations, and so on, simulations as well. So they will tell us, like, what are the challenges in their field, what are the demographics in their field. So I think this will be very interesting. And also for young early career researchers, students who want to know about these fields, so you can talk to the experts as well. And finally, the last session in this event will be an interaction session where we will have early career researchers who will tell you more about their career path, about their lives, and how they have been dealing with different challenges in gravitational wave astronomy. So if you want to ask questions, then please be there at the interaction session. So I think it was great to have all of you with us. So thank you, and I hope I will see you tomorrow again.
yeah, thank you for joining, and see you all tomorrow.
Thank you
again.
so much.
See you tomorrow.
Yeah.
Huge thanks.
Thank you.
Thank
Bye.
you.
Bye.